even kijken. We hebben while loop is dat. Oh nee, dit is if. If they want. Excellent conditions. Je kunt even er doorheen praten.
Ja.
Voor de lol.
Test 1, 2. Ja. Hey, hey.
states it's about something linear solve or something, but
No.
at the internet it's combined stochastic.
Yes. So this is what is on the internet is the
Is the truth.
updated.
This is the ground truth. Okay. Okay. Thank you very much.
You're welcome. Okay, I'm on pre-prod. Okay. So here is also your slides. I got them. So we don't need it yet. So thank you.
Okay, great. So, yes, perfect.
Okay, now we're
Stream on.
Okay,
Go thumbs up. We can start.
okay, well, can you give me the mic? Is it Javi?
Diego.
Yeah.
Diego Cera.
Okay, great. Thank you. Sorry for the delay, but now we will start our session, and the first talk will be a lightning talk by Diego from, he was associate professor at the Université Paris, and he will present to us his Mitas evolution.
So, good morning, everyone. Today we'll present my package Mitas and the new features for the last release 3.0 in this week. So, Mitas is actually a package for working with protein sequences and structures. So basically, proteins are the main machinery in the cell that performs all the functions that keeps all the organisms alive. And in particular, we can think of a protein as composed of a sequence of amino acid residues that determines a structure or a series of structures in the three-dimensional space that finally determines the function of the protein in the cell. So Mitas offers the MSI module that has ways to represent protein sequences and multiple sequence alignments. The PDV module for working with protein structures, and the and the information module for working with evolutionary information as conservation and covariation can give us a hint about the function of a protein. So in the last year, revolution has happened because of AlphaFold 2 in structural informatics, because now we can predict very accurate structure for proteins using simply multiple sequence alignments. So that has allowed us to go from 200,000 proteins in the PDV database to 200 million proteins in the AlphaFold DB. So to access all this information from Mitas, now we have two functions. We have the download AlphaFold structure function that takes an UniProt accession that identifies the protein and downloads the structure for that protein from the AlphaFold DB. And also we have a carry AlphaFold DB function that is going to perform a carry to the AlphaFold DB API, and it's going to return a JSON object that we can use as a dictionary to get more information. So for example, here, if we want to see what is the quality of the model, we can try to see the PAA matrix, and we can get the URL from that. So also for integrating Mitas in pipelines that use AlphaFold 2, we have added some new functionality to the MSA module. So one of the functionality is that now it parses read and write in I3M formats. That is the format that is used by AlphaFold 2 and CollabFold. So now you can use it, for example, to analyze the multiple sequence alignment that AlphaFold has used for predicting the protein structure. And we also have, in order to test different things about and to generate variability, for example, in the structural models, a new shuffle MSI function that keeps the reference sequence untouched, but allows you to, for example, shuffle only a subset of columns of the multiple sequence alignment. And also very important when trying to predict protein-protein interactions, we usually create concatenated alignments in which we match in the same row sequences that came from the same species. And in order to make easy this process, we have now the join MSA function that is going to take the two multiple sequence alignment and a list of pairs of a dictionary of the indicating the pairing of the sequences in the multiple sequence alignments. And it's going to create these concatenated alignments for AlphaFold 2. So now also we have biostructure support in Mitas, thanks to now biostructure is very lightweight, thanks to show, thanks. So Mitas now has a dependency biostructure that allows to, for example, read and write MNC file that wasn't possible before. Now it is also the default format for Mitas, so when you download, for example, the structure from AlphaFold DB, it's going to be downloaded in the MMC format. And another thing we add is a way to convert between the vector residue, PDB residues of Mitas to the molecular structure of biostructure from Biojulia. So that allows to use to go between the two structures in order to expand the utilities to use other packages of the Biojulia ecosystem. So, for example, here we have an example of going from a Mitas structure to a molecular structure of biostructure, and then using the extension of biostructure for data frames that converts the structure to a data frame object. So if you are used to work with with the structures as a data frame, you can use that. So for concluding, Mitas 3.0 has many functionality to work with the state-of-the-art tools. Here in the talk I was mainly talking about AlphaFold 2, but also it integrates things to work with FoldSeq. And in the future I would like to expand the integration of Mitas with the Biojulia ecosystem, and also with the available GLL packages for external bioinformatics tools, as for example MAFT. So thank you all for your attention. I will be glad to answer any question you may have. Yes.
I'm not familiar with Mitas. Does it also include functions for... Thank you. Does it also have functionality for plotting structures, visualizing structures, and working with structures visually?
So for visualizing structures, there are a very basic plot recipe that you can simply use plot and plot the structure or the multiple sequence alignment, and it's going to show a very basic representation. However, in the ecosystem there is something that is better, that is Biochemical, that allows to represent the structures in a more beautiful way and interactive way, and also the multiple sequence alignment. So, but you can use it also with Mitas.
Thank you.
Thanks, great talk. You mentioned fold-seq. How does that work? Do you use some binary or something to run fold-seq?
Yes, FoldSeq is already available as a GLL package, so you can install FoldSeq GLL to install it and run it from that. Basically, the new things in Mitas for working with FoldSeq is mainly the ability to parse the PDB structures that FoldSeq generates. For example, when you carrying the AlphaFold-DB, this is a very large database. It only stores the alpha carbons, and the PDB format it outputs is not very compliant. So now they can parse also this output, but in fact you use it as an external tool. So thank you very much for your questions.
Yeah, let's thank the speaker again. And Vincent, you can come to the stage. Okay, next up is Vincent Wieland from the University of Bonn, and he will tell us about the combined statistic models for the evaluation of cancer progression from clinical data. Thank you.
Yeah, thanks very much for having me. Yeah, I'm Vincent. I'm from the University of Bonn, a PhD student there, and I started last year. And my main project then developed to be some kind of a collaboration with the university clinics, and they want to evaluate cancer trajectories, so cancer patient trajectories, so really look at what is the trajectory of a patient as a whole on a holistic level throughout the course of disease. And there's some challenges and shortcomings so far in the cancer research for that. So first of it, survival analysis is what you will mostly see if you look into cancer trials. Clinical trials are costly. They have a lot of ethical regulatories, so we don't want to use this kind of nice structured data because it's not available for them. They really want to use what is out there in an unstructured way when patients come in for screening, for diagnosis of cancer, for if they are in the hospital. There's a lot of routine data which is unused because it's unstructured. But this routine data contains a lot of information about various processes which are going on in the cancer patient, and we then try to combine these processes into one kind of model. So what we want to do with this first work is to look at three different processes, combine them into one, do some parameter inference for the parameters coming up there, and see whether we can explain the trajectories and really the dynamics we see in the cancer patients. Of course, this is kind of a high goal, and today I just want to present the first step towards it, and I'm also happy to get a lot of ideas from you for the next steps into that direction. So when we start, the first question is, okay, how do we model a cancer patient? And of course, there are many different things we can model, but the first three we considered as really important were first the survival of the patient. So what you will see, a patient with cancer dies at some point. This is why we want to treat them. This is why we need to develop new therapies, and we need to model them, and they die because of the disease. And this disease is characterized, first of all, by a tumor which grows inside a cancer patient. So here maybe the example of some breast cancer patient. This tumor size we want to describe in some way. And then the second really important characteristic of, in this case, breast cancer is that it metastasizes. So there's this famous quote, 90% of death related to cancer coming from metastasis. There's no data validating this quote, but this quote is cited a lot in cancer research. So it shows that metastasis and the spread of metastasis is really a threat on the patient's life. So we chose these two as describing the disease, and then the survival as our outcome, which we want to look at. So let's dive a bit deeper into that. So the first is modeling tumor growth. There are a bunch of models out there and a bunch of literature, but if we start simple, then tumor growth is just a continuous process. So we are modeling, for example, the size, the volume, the diameter of a tumor by some kind of differential equation. And if we take it simple as we want to, this differential equation is just an ordinary differential equation. We have one growth factor, beta, and a function which accounts for like deviating from exponential growth. But the really most simple thing is, and what started in the 50s, is modeling a cancer tumor by exponential growth. So this will be the first example we consider. It has a lot of limitations, we can tell you, but it's quite valid still if the cancer is still in its early phase, limited time frames we look at, there's no restriction on resources. But if there are restrictions on resources, we can then use a second growth laws, for example. So Grampert's tumor growth came up in the 60s and said, okay, we have this additional function, logarithm of carrying capacity times divided by the size of the tumor to account for like resources in the body being limited. Cancer can't grow larger than a certain threshold. So these two differential equations expressions are quite nice because they have solutions, but you can also put in there other growth laws if you like. The second part we want here, we don't model yet the spatial resolution, we just model the number of metastases. So we have some number which is there at the time point of diagnosis, and then we have a inhomogeneous Poisson process, so just a counting process, counting the number of metastases, and the intensity rate for this process now depends on time and on the size of the tumor. So there's the first combination we take into account. If we then look at the likelihood later, we will see, okay, this is quite a nice formulation, because what we can say is that if the probability of some number n new metastases in a certain time interval is just a PDF of Poisson process, and this PDF has this accumulated density here, so the only assumption we need on our model is that this integral somehow exists. So we need to have a nice functional intensity rate that can be integrated over time intervals. And the third process, not the third process, but the examples for this would be really the most simple thing you can think of, just a volume-based metastasis intensity. We have a base parameter plus some parameter times the function of the size of the tumor. In this case, square root can also be something else. Square root just showed some nice robust behavior. And then we also see that dependent on the size of the tumor or the tumor growth law, we get different trajectories for our metastases. There's also a bit more sophisticated method in thinking about metastasis expressed. So for metastasis to be able to successfully invade a new environment, it needs to be highly mutated. And mutation of cells can only occur if cells divide. So we can also think about expressing the rate for metastasis to be successful in a new environment to depend on the number of cell divisions, which is just the logarithm of the number of cells. So volume of the tumor divided by volume of the single cell divided by logarithm of 2. This obviously nothing we came up with. It's used in cancer literature, but we can also insert this into our model, and then we also see different trajectories. If we just take an exponential tumor growth law and then different metastasis growth laws, metastasis spread laws, then we get different trajectories for that. And the third process is the patient survival. So for the patient survival, the thinking was, okay, now this patient survival should depend on the size of the tumor as some integrative measure, how far our disease is already developed, and the number of metastases. As I said, metastases kind of pose a threat on organs, and this causes a lot of death. So we really want to take this correlation into account. And since cancer patients mostly die because of the disease and not because they are already old, we also can say that given we survived until some time point, the survival of the next sometime really does not depend on how long we already survived. So this is kind of the memoryless property, and this translates then in mathematics to the exponential distributed survival times. So when we look at the probability to survive until some time, it's again involve exponential function over this accumulated intensity rate. So again, we need some assumption that this death intensity rates are integrable over time intervals. You can think then of the death process as a Poisson process, which just stops after the first jump, because if the cancer patient is dead, the process stops. But we have, and then it's again a Markov process, which is mathematically speaking quite nice, but just thinking about Poisson process stopping it after one jump. And as a simple example in this work, we can consider just really the most simple thing we could do, a parameter times the size of the tumor plus a parameter times the number of metastases. And if we then put in, for example, different tumor growth laws, we get different Kaplan-Meier curves, so different survival probability curves for our patients. So then we said, okay, now we need to look at all three of them combined. So our picture from the beginning would then be fill up. Let's say we have a continuous growth process, we have a Poisson process for metastasis number and a Poisson process for the death. And then we were thinking, okay, now we can formulate this, we can simulate this, and then we want to leverage data. So what kind of data we will leverage there is just, okay, we have some irregular, they look quite equidistant here, they are, but in practice they're not. So some irregular time points and at which we observe the size of a tumor, because there might be some screenings, there might be radiological data. We will observe the number of metastases, and here it's quite the first tricky part, is that we just observe the number of metastases at some time points. We don't observe when this jump happens, so when does the new metastasis occur. So the time points are really uninformative, except for the last one, because what we also assume to observe is the death time point. I mean, if a patient dies, you will recognize quite quite quickly. So these are the three processes. Then we said, okay, and this S, N, and D now make just one vector X, and this is our process. We are looking at our combined stochastic model. In practice, then, what one wants to do is we have now a model formulation, which involves a lot of parameters, intensity rates, and so on, and we then really want to find out what are these parameters for different patients. So we want to do some parameter inference. And for this to be efficient, because a physician doesn't want to wait 2 weeks for results, we thought like, okay, the most efficient way we can think of is really formulating a likelihood function. So when we look at this, it's kind of a hidden Markov model what we have if we discretize it over time. All processes are Markov processes, so we can look into the formulation of a likelihood for a hidden Markov model. And what we then want to say, if we have a data set consisting of L patients, we really want to get the marginal likelihood for each patient, so marginalizing out our hidden dynamics. The first one are assumptions on the observational model, for example, additive Gaussian noise on the tumor size, because we have measurement errors or so on. So this is kind of model choices we can make. And then the last part, we can, for each patient, again, split over time points. And what we really left with is these transition laws. We need to somehow write down what is the state of the patient at the next time point, given we know what it is on this time point. And then you can do a bunch of calculations, and we have this process formulation. It's really nice. And at the end, it comes to these nice, ugly nested integrals. So they're really nasty nested integrals, as I like to call them. And the idea behind these integrals for the death process is, okay, since we don't observe when the metastasis is there, we just see, okay, we have M new metastases. We now need to integrate over all possible time points at which these metastases could have occurred with times the probability that they occurred exactly in this order at this time point, and so on. And this gets quite challenging, I would say. But at least we could formulate a formula for the likelihoods depending on all these weights being just functions that are integrable. So we then said, okay, let's do simulation study. I showed you some examples of processes we wanted to consider for the simulation study. So we took 3 models, precisely the exponential proportional model. We have the exponential tumor growth times our volume-based metastasis, the cell division model, where we changed the metastasis spread now by this division-based, and there we already see for this exponential tumor growth, our number of cell divisions gets quite a nice formula, because just beta times time divided by logarithm of 2. And the last one is the Gompertz model, where we exchange the exponential tumor growth by the Gompertz growth with the volume-based metastasis intensity. And for all 3 processes, or for all 3 models, we just took the same simple example for the death intensity. And the first result for that is, and I found it quite nice when I discovered it, because I did a lot of calculations, we get analytical likelihood formulations for the first 2 models. This is quite nice. Of course, I didn't get them by hand, writing down pages of pages. Mathematica get them. And I can tell you just, like, one equation for m equals 5 is 3 pages in a LaTeX document. So it's quite nasty, but we get them. And this means we have a nice speed up. Speaking about Mathematica and implementation, maybe a first side remark: the implementation of simulation optimization is, of course, done not in Python but in Julia, otherwise I would not be standing here. And for this, it's quite nice to use Julia, and it was our first choice because we could express differential equations in this nice SciML ecosystem. We could write our own simulation algorithm for jump processes and then use Julia's modularity to combine them nicely. This works really, really well. And for the optimization, we hard-coded analytical expressions, or ChatGPT does. We approximated the nested integrals if we don't have the analytical expression by a cubature package, so by some adaptive quadrature rules. And then if we have forward-diff working on our expressions, we could use LBFGS. If not, we could use simulated annealing both for the optim.jl package to do the parameter inference, so optimizing our likelihood function. Here's also a side arrow because for some of these expressions, they involve functions which are not able to get derivatives with forward-diff, unfortunately. And then we can also do this quite in parallel. So we saw we can split over patients, so we can do the likelihood calculation for each patient in parallel to speed things up further up. And Julia does it automatically, or we use distributed. So it's really a nice task for Julia programming language here. Okay, now getting to some result figures, actually. Since we're in systems biology, we like figures, so I will show you some. The first thing we needed to make sure is that our analytical likelihoods and the numerical ones, like a sanity check, they agree with each other, and of course they do, otherwise I would maybe not show it to you. And then we also saw that analytical likelihoods are really giving us an efficiency gain. So for the exponential proportional model, this efficiency gains is nearly 2 orders of magnitude. So it goes from some microseconds to like microseconds for the analytical times to microseconds for the numeric times for one evaluation, so it's really a gain. For the cell division based model, there we have not such a huge gain, but still this is due to it involves an upper incomplete gamma function, which is also under the hood approximated numerically in Julia, so we don't get this huge gain. We also don't get gradients, but still 5 times faster is quite a thing if you want to do this for a lot of patients. Obviously, this then translates also into optimization. So we use the simulated annealing on the numeric and the analytic likelihoods and the LBFGS if we have gradients. And then if you look at the optimizer traces, we really see how they cut down, like from going 10,000 seconds, so nearly 2 hours, to like 10 seconds for the exponential proportional model, which is quite nice because then you can do a lot more stuff in practice than just always waiting. For the cell division model, we don't have gradients, so we don't get the huge speed up. We're working on the gradients here. But still getting nearly 1 order of magnitude means really reducing the time we have to wait. Obviously, all the likelihood calculations are nice and efficiency gain is great, but if the results are not correct, we don't do anything with them. So we really wanted to show that we get accurate estimates, and what you can see here, we also did some sampling to get confidence intervals for our maximum likelihood estimator. And what we saw, which is quite nice, is that all these confidence intervals always cover the true values we put into our simulation study for the 5 parameters involving in the rate and the growth for the exponential proportional model, and also for the cell division model we got this nicely accurate parameter estimates. So it's kind of a working framework. Then another thing we were thinking about is, okay, now in practice we don't really know which law is really accounts for the metastatic seeding in the patient, so we wanted to do some kind of model selection. So we simulated forward exponential tumor growth laws twice the same, and then put the volume-based or the cell division-based metastasis process on that to get 2 different metastases curves, and we chose parameters to be like that also the death process gives us really similar Kaplan-Meier curves, so the only difference in the data sets is really in this metastasis processes, and then we fitted both models to both data sets to see can we identify which model is accounts for which data set, so which data set is created with which models, and we can, because if we then calculate the AKIK information criterion and we take the difference, we see that for the proportional data, the proportional model is the better one, and for the cell division data, the cell division model is the better one, and by quite some difference. So normally you say it's statistically significantly different if it's more than 10. We're ending up at 300 or 1,000. So it's really quite sure, okay, this is the data which, or this is the dynamics which accounts for this data, which is quite nice. You can do the same simulation for the tumor growth laws, but using ODEs, this is not that interesting now, but when we switch to SDEs, this will be more interesting. And the last one, we can also use more complex models. Of course, having this approximation via numerical integration schemes, you can also use the Gompertz tumor growth, and then we can do all the same stuff. We don't see speedups here because we don't have analytical likelihoods. It's just not possible to get this nested integrals done. But we can see, okay, our optimizer, they converge nicely after some time. They all converge to the same point, and we get accurate parameter inference. So we get accurate maximum likelihood estimators with confidence intervals which cover the true values. So it's also possible to exchange this by more complex models. To sum this part a bit up is, okay, we now have a kind of novel approach for modeling a cancer patient with taking into account these 3 processes which are all correlated and combined, and we do not rely on structured data, so we just sampled on random time points for these different processes. We can compute analytical likelihoods in certain model formulations, and if available, they really increase our efficiency. But if not, we can still use the modeling framework to do inference tasks. It is sensitive to model choices, and we can try to use it to identify underlying dynamics, and it's quite flexible, and we can accommodate various complex model formulations. Of course, this is not the end of the story, but just the first, like I would say, first steps we want to do, and the next, even harder steps are then to include covariates. For example, one can think then just adding on this intensity rate some covariate vectors. We really also want to do individual parameters per patient, so really have this somehow maybe functional as in a mixed effect model, being depending on an individual part for each patient being different and a common population parameter. If we did this, we really want to switch to SDEs, or we're already trying to SDEs. So, for example, geometric bound motion as being the SDE counterpart to the exponential growth law, or the SDE counterpart to the Gampert's growth law. But by switching to the SDEs, we don't have analytical likelihoods anymore. I mean, happy if anyone knows how to integrate overall path of a Brownian motion, then I take this. But if not, then we need to think about, okay, how can we like smart and maybe a bit tricky approximate these likelihood formulations. So we still really want to use as much analytical likelihoods as we can, because this gives us efficiency, but then we need to rely on some approximations. So what we already did there is, for example, we then approximated stuff by means or by diffusion bridges and their means and so on, which is working, but yeah, not perfectly yet. And then at the end, we want to use the data we get from our collaboration partners at the university clinics to really see how can we explain this data with our modeling framework. So still some steps to come, and if anyone has comments or suggestions for any of these steps, I'm really happy to take this. Otherwise, thank you a lot for your attention. You can find me. Feel free to contact me after the session or throughout the conference.
Okay, there are a few questions. The next speaker can already put their laptop there. The mic will come.
Thank you very much. You said that those analytical likelihoods meant a huge speed up, but also you said that they are like 3 pages of document. I think it's probably not trivial to have such a long formula and implement it efficiently. Was it any challenge, or was this just straightforward?
Well, I wrote a function in Mathematica, like Mathematica exports stuff in Fortran code, and I wrote a function that exports this into Julia code, and this was quite trivial then to do.
Okay, and like, so I mean...
And then you need to like look on them and add some commas there, like put some plus there, but it was not that bad, actually.
Okay, but I assume that maybe like evaluating certain sub-expressions in a certain order then matters, and so you didn't have to do anything by hand in this regard.
Not that much, really. Just like, I mean, you need to do by hand stuff like that. You need to identify parts where if you might divide by 0 if you go into low number regimes and so on. And we added some log transformations, but it was really nicely getting the Julia code from Mathematica. So I can really, yeah, I don't know, say that Mathematica is nice there.
Okay, yeah, nice. Thank you.
Hi, thanks for the talk. You said you coded your simulation functions yourself with modified intensity functions. Any reason why you didn't use jumpprocesses.jl from SciML?
Yes, long story short, the results were not reliable and correct. I did use SciML there and combined this, and they have a really nice interface there, but then I couldn't get the inference running and for months, and I was like, okay, what happened? And then I went back to simulation and wrote an Euler scheme and this modified next reaction method, and both agreed in the data they produced, but they were different from the SciML one. I have an issue which I will open as soon as I will publish this code and submit this work. I don't know why it doesn't work, really. I really appreciate, I can show you later and really discuss it with you, because I would really appreciate to use this framework, but as soon as you add the second jump process, something happens that it doesn't give an error, but the results are not correct.
Thanks for the talk. Regarding your inference scheme, I'm wondering if you have considered using some kind of simulation-based inference approach, something like a amortized method.
We did, but as long as you have some parts of the analytical likelihood available, our experience in the group was that it's way faster, and so we really changed to getting analytical likelihood formulations with our work. But yeah, it's obviously, if we go to the SDEs, something part we will consider.
Okay, thanks for your talk. My question regarding the start of your talk, so you started with this big vision that you have, but then you went into analytical likelihoods. I'm just curious, why do you spend all this time trying to do this? Why do you know it probably won't scale to more difficult problems? Yeah, thanks.
Well, from my personal view, I think it's always nice to have a starting point where you really can start working and not try to capture the big picture and then like standing in front of a wall when you go climbing and trying to climb that wall and you start to jump doesn't help. So you really start to search for these little knees where you could put in your fingers and then start climbing up. As I said, we extend this now by covariates, individualized parameters, and then we don't get the analytical likelihoods, but doing these computations already gives a lot of insights about how these processes are connected and how the structure is, so which parts we might get analytically available and which parts we might need to approximate and then how to connect them. So I think it's still good to start there at the basement. But yeah, good question.
Okay, we'll stop questions here. Thank you again for your talk.
Thank you very much.
Applaud the art. Okay, so let's welcome our next speaker, who's Jenny Leclerc from the University of Mainz. And she will tell us about the structure-based bioinformatics with biochemical algorithms.jl.
Thank you for the introduction. Now? Yes. Now it's louder, sorry. Then I will start again. But does it work? Yeah. Sorry. So, thanks again for the introduction. And my name is Jenny Leclerc, now with microphone turned on. Classics. I'm a PhD student at the Scientific Computing and Bioinformatics group in Mainz. It's the first time for me at the JuliaCon, so I'm really excited about the whole event, and I hope you can enjoy also the JuliaCon and especially my talk today. It will be structure-based bioinformatics with biochemical algorithms. First, I will give you a short introduction into structure-based bioinformatics. Then I'm going to talk a little bit about the biochemical algorithms library, or short BAL. I will just call it BAL because it's very long. We will dive back into the 90s and see the design goals back then. Then we will look at our new package, Biochemical Algorithms.jl, how we designed that one, and look at the core structures and the performance of some typical tasks. And then I want to show you some applications, so initial things we can do already, and what we are currently working on, and how this all fits into the Julia universe. So I would say we directly get started. Structure-based bioinformatics. What is structure-based bioinformatics? It's a research field working with three-dimensional structures of proteins or combinations of proteins and nucleic acids. And I wrote now the revival of a research field because for some time ago it was getting a little bit quiet in this area because people were turning into proteomics directions, and the main reason why it got fancy again or modern again is due to 3 points in my perspective. So the first one is related to data. As you can see, I put here the plot of the number of released PDB structures per year, and for each different experimental structures. So the PDB is the most important protein data structure data bank. And there were some advances in the electron microscopy area, so that we have more data structures available. But there is also advances in algorithmics that lead to the fact that we have more data we can work on. And this is due to AlphaFold. So both together we have more data available which we can work on. And the other reason why we are really interested in data structures, because I don't know what you did, but a lot of people started in 2020 to sit in their home offices and trying to dock some corona proteins and find a track for that. So first, what is software development in structure-based bioinformatics? It's really a highly non-trivial task, because the things we want to implement, they really need performance, such as structure minimization, molecular docking, or molecular dynamic simulations. And the development of these applications are really, really challenging. So why? Most of the packages were at the high phase of structure-based bioinformatics in 90s, starting from the 90s to 2010, and they are still used up to date because we don't have any more new tools. The performance, as I said, is already required, and the development times shouldn't be that high. It should be actually easy to develop these tools because we need them. And it's dependent on the programming language you choose. Most of the software packages we have in this area focus on one specific task. For example, the implementation of a force field, or the preparation of the molecule, or just for a simulation package. Biochemical algorithms, which are short is for BAL, it focuses on the entire pipeline you can have in a scenario. So it includes basic stuff you can use just to get started. But if you want to use your own force field implementation, the interface is structured so that you can do that. It also comes with a visualization tool, which is called Ball View, that leads you directly gives you an idea how your docking scenario looks like. So I will have to talk a little bit about Ball and C++ code first, because that's how it influences our new design of it. So, but there will also be the biochemical visualization package, which we started to implement. But today we only focus on the left part, so to say. Okay, so BAL, what is BAL? The work on BAL started in 1996. It was majorly published in 2000, and in 2010 there was a major release where they added some good new advances, for example, the Python interface, and they switched to the C++ build system. BAL itself used to have a very large user community, because it is one-of-a-kind package. Even pharmaceutical companies were using BAL software. And this is because it had tools for the entire pipeline. And it's open source, of course. So how is it structured? So you have the standard library, it's a layer structure, and at the bottom you have the standard library, then you have the foundation classes, because if you want to provide software working on different operating systems and on different operating compilers, then you have to adapt your code according to it. And therefore we have some foundation classes that also give data structures for strings and for necessary things like the hash trees and so on. Then we have the kernel, that is basically the core piece of the software, and then we have all the functionalities on top, like a visualization and molecular mechanics pieces. Then on top of that, there resides the actual application that comprises, there are predefined tools you can directly use, or you can try to write your own tools. And on top there's the Python interface that was available since 2010. And of course here on the left you see the necessary packages for the visualization. So this was our C++ library for many years, and it's still, you can still use it, you can download it, you can work with it. That's the kernel. So this is the heart of the software. It's really nicely grafted, by the way. So you use the composite pattern, and every molecular entity, if you want to model that, it's a hierarchical pattern, because you have a molecule, the molecule consists of chains, the chains can have residues, and so on. And this is implemented via the composite pattern. So why I'm only talking now about design goals, a little late after but it's important for the new design. So previously the design goals were ease of use, functionality, openness, and robustness. Ease of use, back then there was the decision to use C++, and it was the optimal choice to implement the software, because we didn't have Julia back then. They wrote an intuitive interface. They provided a lot of functionalities, as we already saw. It is open. You can interchange parts that you want to write on your own, and it is a highly robust library that was part of the success of Ball, because the code is really intensively documented, tested, and corrected for code. But let's look at it from a 2024 perspective. Basically, this is a classic language problem we are facing. So they use C++, and by far it's really performant, but it's not anymore used in the user group. The CMake build system made it easier, but it's still not a trivial task to work with it or to develop your applications. And especially dependency hell if you want to include new libraries. The functionality is still highly required. We need that. There are not so many other options to have this. So that leads us to the introduction of Biochemical Algorithms JL, our new redesign. And it has similar design goals, because we have ease of use, but for us, really important was rapid application development. So the user should be able to directly write down their ideas for a code. And of course, if you're dealing with molecular mechanics, you need efficiency. So why again Julia? It's Julia. Obviously, we all know Julia, we want Julia, it's fine, but just 3 reasons why it's nice to have it for this design. Performance is clear. It solves the 2 language problem, I already said that. And less boilerplate code. So the domain expert should be able to write their ideas down fastly, and it is highly readable. The package manager makes things much more easy, together with the Julia universe. So there are really good packages for specific purposes that we can use already. And one thing that always defines the quality of a scientific package, the availability of documentation, testing, and benchmarking, which can be integrated in a very straightforward manner in our case. So that's were the main reasons to choose Julia. This is a UML diagram for our system. Don't worry if you cannot read all the attributes. The important point here is that our system is at the center. From this, all other molecular entities such as residues, chains, and atoms and bonds are part of it. So I think it's time for a little bit of water, right? Half time. Let's generate some water. So it's just to give you an idea that all the boilerplate is now gone compared to C++ code. We can create our system here. Then we have our molecule. We just create some atoms, set the position of the atoms, create a bond, and basically also can visualize these things. And it looks like our Mickey Mouse that we are always using. It is really straightforward to use. So now a little bit try again. How can we represent atoms and bonds? Because they are the key parts of every simulation, right? Atoms and bonds. That needs to be fast. So the first idea which we had were, of course, data frames. And we implemented that, and it was fairly fine to use. The advantages were very intuitive usage, but for our scenarios, it was just not performant enough. So what we did else then look at was atom space. Atom space is a package from the Julia Molecular Simulation Group, and we were looking at that, and it just doesn't provide all the necessary functionalities we needed. So what we are planning is to be compatible to atom space, which is straightforward. And what we did then is that we used the table.jl interface, which data frames is actually based on. So we implemented our own kernel for that, based on tables.jl, which has the advantage that we directly can convert it to data frames. Sorry, unfortunately the slide is cut, but just to give you some preliminary performance results. If you just plainly write down your code in Julia, it works fine, it works, but it gets, you always have to twiddle a little bit of performance reasons. Yeah, and we did it for the Amber4 suite, we already did that, and for some performance functionalities of the core, we still have to do it. Okay? But it works in general. Sometimes we are faster, sometimes the C++ code is still faster, but yeah, that's the main take-home message. Applications. Let's look at some code again. One thing you always do when you, for example, work with conformations of proteins is that you want to compare protein structures that are similar, that have the same amino acid sequence or something like that. And you can already do that with Biochemical Algorithms.jl. You just read in your data, and then you apply the fragment database, which is shown here in line 3. This is really one advantage of our package, that it provides the code to prepare the molecule, because in the data formats, not all the necessary information is included. Sometimes data is missing. Then you can reconstruct it, the fragments. The bonds are not contained, that's why we have to create bonds. But if you just plainly read the file, then you get a number of atoms here that are, of course, still not connected. Once you reconstruct the bonds, so that's basically what the fragment database can do, then you see the connections, the bonds, you have that. Then you can, of course, compute the RMSD for the two structures. Before we map the structures, it's 5.4. After mapping, it's 1.4. Another application, if you're now interested, okay, how is the energy of the two systems? Are they comparable? Where are differences? Then you can just apply the amber force field. And if you do that with the verbose information, then you get all each of the components, and you can take that and compare it to the other protein structure. So what is out now? What is the next move? What do we want to do? Currently, as I said, we are still looking at the performance to tweak a little bit of performance yet. We want to do scaling benchmarking, so how does it work with bigger inputs? Is it still very good, or what do we have to do to keep the performance? Then we are looking at the PDB reader at the moment, because we need the support from some information that is contained in the PDB reader, such as alternative location IDs. That is still really important. Then we wanted to implement another force field, the charm force field. And then we are looking forward to our package registration that we just started and the official release. And then we head forward to molecular docking and continue to work on the biochemical visualization part. So how does that all fit into the Julia universe? I just saw Joe, you're also here. He's actually you have also a talk, and he's the writer of the MolyJL package, the molecular dynamics package, and I think we can really work together there. We have definitely connections there. And then there's the Proteusyn package that mainly focuses on peptides and modification of peptides and sequence structures. And then there are two big communities, the BioJulia communities we are already using, and the molecular simulation in Julia, where atom space is coming from. So I think definitely we can work together. If you have now ideas, please talk to us. We are here until Friday if you want to contribute, or if we can do something for you, just let us know. We are happy to have more input. And with that, I would like to summarize quickly. So the Biochemical Algorithms JL is a redesign of the popular BALL framework. It attempts to cover the entire molecular modeling pipeline. It is not yet feature complete towards the C++ predecessor, but we are working on that. But it allows for rapid prototyping of ideas, and the design is so flexible that you can implement your own ideas in this interface. Acknowledgements. I would like to thank Professor Hildebrandt and Thomas Kemmer. We are actually the core team behind Biochemical Algorithms JL. And then we have other contributors and the rest of our group that are working on it. And I would like to thank you for your attention. And I'm happy to ask questions if you have any. Thank you.
Yeah, thanks, Jenny. We have plenty of time for questions. So.
Great talk, thanks a lot.
Thanks.
One of the cool uses for this would be kind of setting up simulations which would involve reading force field files, topology files in kind of 1,000 different incompatible formats. So is there any plans for that, or maybe using chem files or something?
Yes, definitely. We are planning to work on that. So the previous BALL library also included that, and we are actually working on it.
Hello, nice work. We are currently preparing a project applications for repurposing proteins of bacteria for food applications. So, for example, whether they're suitable for emulsions or making foam and so on. Could we use your package for that, and what could we do for that? These are all properties that are based on structure, like if they can bind water and how much, or if they can access lipids and so on. And these are things based on the 3D structure, but could we use this suite of algorithms for that?
It depends what you're actually looking at concretely. But in general, yes, of course, you can load your structures there in the PDB format, and also we support 2 other formats. And then you can read it, you can visualize it, and you can make comparisons of that. Or maybe, yeah.
Just quickly answer that.
Maybe we have a microphone? Yeah. Sorry.
Thank you. So where it can probably mostly help you with is getting the whole things connected. So the idea of Ball was never to be the one place that had the world's best, say, molecular dynamics simulation or the world's best docking tool. You have MD code there, you have docking code there, but there are specialized players in that who do that much better. They have much more effort put into it, but you typically cannot just download such a tool and just use it. There's a lot of preparatory work. There's a lot of work going in connecting these things, and that is non-trivial work. So for instance, like when Jenny showed, when you download the structures and all the bonds are missing and so on, you have to recognize what kind of chemical structure that was and to add the correct bonds to the correct locations, figure out what the atom types are, all these kinds of things there, it can help tremendously. So it would probably particularly help you in gluing other stuff together or writing your own code. If you want to work with these kinds of things, if you want to compute forces, if you want to minimize molecules, or if you want to write a docking program or run a docking program or analyze the results of a docking program, all these kinds of things are much easier using this kind of code than doing it from scratch.
Other questions or ideas? Yes.
Is there any electrostatics work inside of
Yes, yes, we have actually, the expert is sitting there. It's Dr. Kemmer actually wrote his thesis about electrostatics. It's called the Nessie JL paper.
It started.
It started.
Started as a way to compute non-local electrostatics because that wasn't really fun to do in C++. And so I mean, the standard electrostatics stuff is, of course, there the Coulomb stuff and so on, but we also have BEM and FEM code for Solvay electrostatics.
Wow.
Do you have
I'm sorry? Can you pass?
So do you have a particle mesh UOD?
Sorry, what?
Not sure if I understood it.
UOD summation, so particle mesh UOD.
Oh, I see. No, not yet. Not yet. Sorry, we don't have PME yet, but it's on our list.
Yeah, so you mentioned minimization of structures. Is that also something that it does?
Yes.
Yeah.
Yes.
So basically all of the things that we can think about.
Yes.
Yeah.
Maybe they are not all yet implemented, but we are working on it.
Structural alignment, so aligning structures?
Not yet. I think
but you're
in the C++ code
yeah.
is not yet ported.
Okay.
Yes. Sometimes we are surprised what Ball offered, to be honest, because it was there for such a long time, and whole generations of PhD students and students worked on it and developed applications because the framework was so open that sometimes even we are thinking, oh yes, there was something.
Okay, if I may ask, how is your experience in migrating such a large code base from C++ to Julia?
Yeah, I mean, once you fight through all the boilerplate, we are just at the beginning, but it feels so naturally to write the code down in Julia compared to C++. It's I mean, we are also. I just gave an experience talk on teaching because we are using our software for 2 years also as a teaching, and the students only know 1 year of programming experience. They are diverse. They have a diverse background. They are computer scientists, physicists, mathematics, and of course biologists. And they started to work with the software, and they were really, really happy and relieved to switch from C++ to Julia and to work with biochemical algorithms JL. So just to have everything together and not being overly frustrated about boiler code in C++.
Yeah, that's nice to hear. Anything you miss from the C++ world?
I mean, it's always nice to have to just get starting and to write down your ideas in Julia, but all the frustration you learned through C++ and setting up software in different platforms, you can learn a lot there, I would say. That is that keeps you busy. It keeps you busy nights and days, and increases your frustration tolerance, but not necessarily helps you in getting the task that you're actually interested in.
Maybe I can add
Yeah.
2 things so maybe just 2 things. One is that, I mean, while Julia gives great performance, the C++ code was pretty performant, but it was optimized over many, many years.
Yes.
And it turns out, as you probably all know, if you want to have really high performant, non-trivial Julia code, you have to do things, and those things are not often straightforward to understand. So you have to learn a different way about thinking of how to make your code faster.
Yeah.
And I mean, that's not necessarily a disadvantage. It's just something that is completely different than it was. And most people who are new, in our case, are new to it, don't understand it yet. The second thing, the only real thing that is maybe, I don't know, maybe just a little bit scary. I mean, there's so much great stuff in Julia, so many great packages. What is often a little bit unclear is if we can rely on them for a longer time. Because, of course, much of it is done in academia, is done through PhD students and postdocs and so on. And we intend to support this for a very long time, like we did the last thing. And we don't want to reinvent the wheel all the time. So we want to use all these exciting packages in Julia. But there it's, you know, that's something that we have to figure out, where we can rely on it or where we need to have a backup plan or whatever.
Mm-hmm.
I mean, one possibility would be to help maintaining then.
That's, yeah, I mean, for things that are really important. For things that are really important, that's probably what's going to happen, yeah.
Great. So thank you for your talk. It was
you.
really interesting. So one round of applause, please.
Thank you.
Okay. Yeah. So let's welcome our next speaker, who is Harry Sexton from the Sheffield University. He will tell us about the personalization of cardiovascular models using Julia. So go ahead.
Thank you. So So I think this talk is slightly more high level about we're just starting a new project. We're interested in this, as is everybody in the NAN, this application of digital twins and personalization. And it's more about the application of the methods rather than there is obviously a physiological focus here, but it's just kind of saying, okay, if you're looking to develop this pipeline, how Julia's kind of already there and ready for us to start implementing these things. So our focus is on pulmonary hypertension and on trying to simulate global dynamics. So we focus on these lump parameter models, which just give simplified representations of the cardiac system. See, we've got 4 chambers, ventricle and atria, with systemic and pulmonary circulation. And hypertension would typically indicate an increased resistance around the vascular bed or the arteries. So the aim is saying, okay, can we develop these models that they can get even larger in size like this, or even one for the venous system, and they can eventually get really silly in terms of size. So it's about saying, okay, how do you strike that balance between ensuring you obtain these key biomarkers that indicate pathophysiology, but also a good enough representation of the anatomy. So you can combine representations of the legs, like we've got here, with 4 chambers and see what happens. So what do these model components mean? The resistances are viscous dissipation. So if you've got arterial blockage, indication of a resistance, i.e. some pathophysiology there. Inertia, represented by an inductance, and then vessel distensibility, so how much does an artery contract and release. So quite intuitive representations of each compartment. So what do we mean, I think, first by personalised medicine? It's about this, I think, it's about the combination of both model and data. You've got to say, okay, is the model parameterized by these biomarkers? Are the values realistic? And the model gives you something back. And what does it give you? It gives you these indicators of pathophysiology. So venous compliance, systemic resistance, pulmonary resistance, but then also the data. It's what can you obtain clinically? What describes that patient's physiological state? And the combination of both of these eventually produces this personalised medicine. But if we start to carry on and develop these really complex models, they might go from subcellular level to organ level. What can you do offline? So without this straight jump to patient data and say, okay, well, how quickly can I just ram as much data into my model as possible? What can you do in terms of, I think this is the real big one and the real stopper for clinicians in my experience, is about this risk prediction. What's this uncertainty associated with any predictions that you're going to make? What's the uncertainty associated with you saying, okay, this is a biomarker of a specific pathophysiological state? So this is the best attempt we've got so far and our finest PowerPoint work at trying to develop this workflow of saying, okay, what can be done offline? What can be done before you end up actually showing it any data at all, to provide this quantification of the uncertainty, along with obtaining a subset of parameters that are constrained by what's going to be available to you. So quite often you'll see people perform in sensitivity analysis and subset reduction with just a choice of outputs that tickle their fancy. However, when it comes to actual calibration of the model with the experimental data, there's a mismatch between that, because what may be available in clinic is not what people have done the subset reduction on as well. So it's about saying, okay, can we combine both the experimental stage and this preparation to create a complete whole model? So I'm going to try and go through going to try and go through the majority of this and just highlight, okay, what packages are available and how they've helped us in the production of trying to generate these personalized models. So, model construction, first of all. What is available? It is a shameless plug. I am involved in this, but we've had nice uptake in the hospitals, especially from clinicians. So, a 4-element wind Kessel model can be generated through these two differential equations. If you were to combine the 4-chamber model and the Venus system, you'd be here a very long time in trying to write down some equations. So that's how it might look in MATLAB, where you just write your differential equations and solve them. But what's the jump that we made in into Modeling Toolkit? It's been able to define the old, been able to define individual compartments just through individual segments, and then combining them based on whichever direction the flow may be going. So it takes its inspiration from Simulink and A-causal modeling as Modeling Toolkit in just providing clinicians with this, okay, drag and drop representation. Because we've now got cardiologists who are almost see it as a little game in saying, okay, can we reproduce bits of the cardiac system? Can they put together some sort of circuit that gives them values that they've observed in clinic? And writing out the differential equations was absolutely a no-go. But when all they have to change is which compartment and the direction what it's connected to, it makes it a lot easier for them to get on board. What does it have available to you built on top of Modeling Toolkit? You can link to SPML, CellML. There's a whole range of nonlinear compliance, valve functions, and then 3 heart descriptions as well. And we're constantly trying to build upon this to get more and more, as ones pop up in the literature, try and get them imported in. Global sensitivity analysis. Why is this important? So this allows us to then obtain, okay, what's the risk associated with any predictions? So we're saying, okay, what are the impactful parameters that contribute to the outputs that we've got in our system? Allows also for what's the word I'm after? Confidence intervals, so you can do bootstrapping, resampling with replacement, that allows you to say, okay, how confident are you in your global sensitivity analysis results? Which is something that is vital in this, being able to provide that. It all comes back to this quantification of risk. What's the risk associated with any predictions you're making? And then also gain physiological insight. So this is just another, it's all really stems from the Sobol indices that you can obtain. And this is then the 4-chamber model, a more advanced one that I showed before, that's popular for benchmarking and things like this. And if we need to perform a sensitivity analysis, we need K P plus 2. So P is the dimension of the input space, K is the number of samples that you've got. And I'm going to show some quite typically Julian showy-off kind of metrics about the differential equations, but there is a point to this. So if we wanted to do this in MATLAB, Python, CellML Toolkit, what this is about is this reusability, so this standardization between the fields. So this, the model I showed before is on CellML, and then from them you can go, okay, click, download the code, run the code, get the outputs. And that's what the people who do the clinical work are interested in. And so what these are metrics for doing that exact thing of I go to CellML, I download the generated code, and I click run. And no way in hell do I believe that if anybody wrote their own script, that would be the result. But the people we're trying to engage with are not software developers. These are clinical personnel. So you can see straight away in terms of performing the sensitivity analysis, if you need to do millions of runs, we're way up on what's available out there for the reusable and standardized metrics so far. And this is just another quite example for why this is important. So the solid lines are sensitivity metrics, and along the bottom this would be increasing sample size. Investigations have been done about, okay, what are the sensitivity indices and their convergence. You see, the typical literature value for this sort of thing is where the red line would be, and people would take their sensitivity indices at that point. But for cardiac models associated with the nonlinearity, the stiffness and things like that, you've got to go a lot further on. So essentially this whole thing boils down to how quick can you solve the thing. And I'm not here to parrot the differential equations, but for from a clinical perspective, this allows us to do the quantification of risk better than what tools have been available so far. Subset selection. So if you're interested in a pulmonary hypertension, for example, and you've got a set of outputs, you do the sensitivity against a set of outputs. How do you reduce, if you've got 60 or 70 parameters and you've only got 3 measurements, well, good luck trying to obtain some sort of identifiable insight into that. So it's about saying, okay, how do you obtain this subset in that can be personalized to the clinical data that you obtain? So E represents, quite unintuitively, influence. D is the orthogonality, and I is this, what they call this identifiability index. And this is about saying, okay, can you rank the parameters and give me the best group of parameters that are not only influential, but they're also orthogonal. So the idea behind that is saying, if you've got a response surface for a set of outputs, you need to make sure that the influence of the parameters is orthogonal. So if I stand behind somebody and we both throw a ball in the same direction and somebody turns around, you've got no way of understanding who threw a ball the furthest. So you need to be able to differentiate between the parameter effects as well. So them just being influential doesn't always cut it. So there are functions on the Global Sensitivity Analysis GitHub page that do this. I just need to refactor them into the way that is deemed appropriate by the higher echelons. And then uncertainty analysis. I will die on the hill that there is a difference between uncertainty quantification and uncertainty analysis, because sensitivity analysis is a practice of inputs. So it only cares about the inputs. It tells you, okay, what inputs are influential on the outputs. You've got no clue that the bounds you prescribe to a sensitivity analysis give you physiological outputs. There's no way of, to date, as far as I'm aware, there's no way of knowing that that's true. So what uncertainty analysis does is says, okay, given some sort of bounds that you put on the parameters, what are the maximum and minimum outputs that you get? So for example, for us, if we end up with a maximum ventricular pressure of, I don't know, 10 mmHg, well, there's no point us even exploring that region of the space, because anybody who's got 10 mmHg is brown bread, dead. So that then gives us a great way to do this. So we can do this through measurements.jl, linear propagation of the errors. So this is really helpful for medical device errors, where we know that there's kind of a consistent level of error associated. So you can just propagate that error through. It makes things really helpful. Monte Carlo measurements, if you move across to a more statistical approach, you can do the distributions of numbers, so it makes it a lot easier when trying to explain to clinicians that about the adding and subtracting of distributions and things like that. And then probnum diffq allows us to solve these and compute posterior distributions as differential equations. Kalman filtration, so this is all about saying, okay, once you've obtained this subset of parameters, and you know that you need to then begin to calibrate this against some patient data. How do you go about that? So there are a host of control packages for data assimilation that exist out there, and I think they've all got the benefits of. They've all got drawbacks and benefits. So I think the best one that we've found for this application so far is about the low-level particle filters. So these, the valve functions are and the resistors obviously are algebraic equations in our models. So being able to represent and do a data assimilation problem for differential algebraic equations, that's always a really big help. But then also, I've recently come across a new method for data assimilation, which is about implementing it as a callback. So quite often when you're performing the data assimilation, there's discretization to either an Euler scheme or, if you're lucky, a Runge-Kutta 4, because nobody's going to be writing n order steps. But what the callbacks allow you to do is to leverage the higher order solvers, so the Verne 7, the Verne 9s, but implement it at each time step. So you get the higher order accuracy of the ODE solver, which normally would be lost in data assimilation problems. Yeah, so and this is where I think Kalman filtration for the personalization just is a really intuitive thing. It's just about the combination of, okay, what is the prediction, what is the experimental data you've got, and give me your best estimate for this personalized subset of parameters. Profile likelihood, and big shout out to the workshop yesterday, which I'll try and beat him into putting into a package about profile likelihood. So far we'd come across profile likelihood and likelihood profiler. These do all have drawbacks, which I don't think yours does, so please put it into a package, please. And that gives us then some insight into the identifiability of associated with the parameters that you've obtained. Subtlety involved in this. The profile likelihood and optimization tell you slightly different things. So what we've done here is we've done an identifiability analysis, but in a theoretical sense. It's saying, okay, in the best case scenario, what are the subset of parameters that you're going to obtain that will give you insight into the information about that patient? And then when we eventually do show it clinical data, when we do show it the clinical data, the optimization is just giving us some sort of parameters. We've got no clue as to whether they are identifiable, whether they are unique. And this is where the profile likelihood comes into play. Because then we can see, okay, theoretically we've obtained the best subset of parameters. However, practically, when you've got the noise of the data, you've got the measurement error from the machines, is that subset of parameters still identifiable? And any issues with any identifiability then can be attributed to measurement error, noise error, things like this. Yes, before the big sell. So that's that. And this is obviously an iterative thing. This is not a one-time job. I think the majority of the creation of the model is good, and that should be reused, but it's important to acknowledge that you're consistently constrained by the experimental data that you've got available. And every time there is a new data, this is a new dimension, you need to go back and do this whole process again. So this is then the big sell, this CVD net. So I'm starting a postdoc with Imperial, Sheffield and Nottingham, so I've been rolled out to do the cell. And it's all about the personalization of pulmonary hypertension patients. So we're looking at saying, okay, over a 5-year period, can you observe deterioration? And we've got an abundance of kind of horribly invasive data and things like that. So if anybody does know anybody that's interested in a job, please do come and speak to me. Yes, thank you very much. So that is then a QR code, I think, for any of the literature that backs up some of the subset selection and things like that. But I'm more than happy to converse over anything. Okay, thank you very much.
Thank you for your talk. Are there any questions here?
It's lunchtime.
Yes, thank you very much for your talk. It was very interesting. I was wondering, I imagine it could be possible that you would find multiple subsets of parameters that would provide you with a similar, or at least would be good. How do you choose between the subsets?
So that is true, but this is supposed to alleviate that essence of choice. There is because it's trying to remove that. Okay, I'll choose this, I'll do this, as much as possible. With this algorithm, the only one choice that you have to make or put is that the parameter which comes out as the most influential across all the outputs, that goes in first as the identifiable starter of the parameter. And then from that point, it's a recursive algorithm that you make no choice in. That you say, okay, compute the orthogonality of that against all the other ones, multiply it by the influence, whichever's got the highest identifiability index, that then goes in. And then do that against them two sets, against the other ones. So it's computed through a linear span, so you compute. It's the linear orthogonality between the chosen ones and the ones that remain in the set. So it alleviates that essence of, okay, do I have to, which ones do I choose? What level of cutoff do I put? Because this is all, there are obviously definitions for these, but they're all normalized between 0 and 1. So you can essentially, the set that you end up with, as soon as it starts to get towards like 0.05, well, that's a 5% chance of that being identifiable theoretically. Whereas the ones up the top are 99, that kind of business. So the answer to your question is this method alleviates that choice of subsets. There are other methods out there, which one is called a structural correlations method. So that's by a group in America, and that is more clinical choice. So saying, okay, you obtain multiple subsets, pick the one that looks clinically the best, kind of thing. So it's swings and roundabouts.
Thank you.
If there's no further questions, then thank you. And thanks to the speaker again. I hope you enjoyed this session, and afterwards there will be lunch. So enjoy that too. Thank you.
Thank you so much. Oh, the microphone is working. Nice. Yeah, I'm really glad to be here in person. I think every second person I met here was telling the same, that it's so great to see all the Julia developers in person instead of just seeing GitHub handles. I'm from Kyoto University and I'm a mathematician, but at the moment I'm in an institute for human biology, which is great for me because they only care that I make pretty simulations, and that's what this talk is going to be about. And yeah, let's start. So I want to talk today a little bit about agent-based modeling, but slightly from the perspective of which challenges do we have in developmental biology. And that's mostly picture show. And then I have two packages which are relatively small packages. One of them is focusing on making agent-based models on the GPU faster. And the other one is just a very small helper tool I needed and made into a small package. And in the end, I want to give an outlook on things which I'm planning to work on at the next time. And I think I'm very curious about feedback, like advice or seeing connections to other Julia packages and seeing what's already there. So feedback is very welcome. I can actually present the main part very quickly. So the package which I'm going to present is going to actually have only two functions. So the package I'm showing in the end is going to deal with positions X and how we can find neighbors within a cutoff region of from these positions. So it's very straightforward code, and basically my contribution was to make that GPU capable. And yeah, so that's the one slide overview of my talk. Now, let's go to the first part about developmental biology. So an introduction to agent-based modeling is really difficult, and some of the experts are sitting here in the audience, not me. So I understand agent-based modeling a little bit as you consider a lot of agents. They can be pedestrian cells or anything which is somehow an individual unit. And then you want to figure out how do they behave together based on the interaction laws. So here this is some simulations for mesenchymal cells where we thought, okay, cells somehow they link to each other, and then depending on that they maybe change their polarity, so the direction in which they walk. And in this kind of simulation here, the cells somehow collectively move from the left to the right, even so the interaction laws are completely symmetric in a certain sense. And such behavior can be studied with agent-based models. And I don't like agent-based models actually, because I think they're more like a last resort. So usually you would like to use a nice physical model if you can, but often especially in biology, things get messy and complex, and agent-based models are like one resort to deal with such complexity. Maybe not everyone knows what developmental biology is about, so I will give also one slide introduction to that. In developmental biology, we are interested basically how a chicken turns into an egg. And that is a process with a lot of intermediate stages. So first you have one cell, it turns into a few cells. At some point they figure out what is up and down, and then they figure out what is my spine and all of these things. And they are very complex cellular processes underneath. And it's quite clear that capturing each of these stages is borderline impossible with like nice physics model, because there's genetics going on, there's like interaction between like phenotypes of cells are changing, and there's the mechanics between cells. And we cannot just put all of that into a model and hope that it works. We somehow have to make assumptions. And in agent-based modeling, we can, for example, focus on part of these stages and then say, oh, we think it works like this. Does it work in the computer? Okay. Let's hope that we survive. So now I have a few videos, and these are basically all 2-year simulations which I did in the last 4 years. So the first project was on something called epithelial to mesenchymal transitions. That is basically like the abstract term for example, skin cells turning into cancer cells. And that was the start of my PhD, like 4 or 5 years ago, where I rewrote Fortran MATLAB solution into Julia. And that was a really good decision, as a lot of you would probably also agree. It saved me a lot of mental pain, and in particular, everything became a lot faster because you don't have to translate your Fortran simulation into some files in between and load them in MATLAB and all of these things. So I was really happy of going into Julia, and basically the pandemic was for me a time where I spent 50% of my time online checking the Julia forum, which was also a good time. So this is, for example, one of the simulations I was working on for an epithelial tissue. So that is something like skin. Here the visualization is with ParaView because it's quite old. Nowadays, of course, you can use Maki. But translating this just worked out well. And here I want to talk a little bit about, okay, what are the challenges from biology? In biology, one of the challenges we faced in this problem is that usually you have a model and you want to find parameters. So that's kind of like, there are a lot of talks here about finding parameters, but here in this particular challenge, the biologist was like, oh, actually I have 5 parameters, and for these 5 parameters I want to try all combinations. And why do I want to try all combinations? Because the biological cells just are like this. So cancer cells are so difficult to treat because they're heterogeneous. If you have 2 cancer cells, the chances that they are very different are quite high, and that makes it so difficult to treat them. And that makes experiments also challenging. So in this particular project, the challenge was that we want to explore all the parameter sets and not just applying like parameter optimization techniques or something. So, and that requires speed. So here a few numbers, basically the previous solution. In the end, we needed to run 150,000 simulations, more or less, to get good statistics. And then you can see how basically transitioning to Julia made that feasible. And that is basically my PhD in a nutshell. Here the lessons learned a little bit is that, of course, Fortran is fast, but Fortran is not fast if you write in every time step a CSV file. And there Julia can very easily save already quite some performance by just keeping it in the memory. And then plotting with GLMaki is fast, which most of you probably know. And then in the end, I introduced some new numerical method, which I found from some NVIDIA researchers, and that really pushed the simulations also further. Let's see at the time. Okay. So yeah, and then basically we used this kind of model and explored all the parameters. In the end, also talked with the biologists who could kind of replicate one of the findings from the simulations, which was really nice. And I think it was, in this case, only possible because of Julia, in the sense that we really could run all of these simulations. So this recently also got accepted. That's the end, basically, of my biology talk here. I don't know how interested it is for you, because probably we all have very different backgrounds. But just to show a little bit where Julia is used nowadays. Here a few more slideshows. Basically, I also use Julia simulations for lymph morphogenesis. So in the center you have our model, and on the side you have the experimental data, which kind of matches in a nice sense. That's what I'm currently working on. And here, of course, like we all know that we can also use the ordinary differential equations package and match it nicely with some agent-based simulations. And then here are some more videos of agent-based models programmed with Julia. With Michelle and Claudia and Sarah and Seren Lee. So this is basically what I'm doing, and now I want to show you one of the tools I developed for that. One lesson I learned, and okay, the authors of Agents JL is here in the audience, so I shouldn't say this, but one thing is that already plain Julia is kind of doing a good job for my task for agent-based modeling, because somehow you can develop very quickly your code, and Julia has all the tools you need, in a sense, to make very flexible simulations. And what I also learned in all of this is writing the simulation is one part, and analyzing this is where 90% of the time goes into. So here the developed ecosystem really helped in the last time. Okay, now to something new. I now want to show an implementation or like how to quickly implement a very simple agent-based model, and one could say this is actually a particle model. So this is a model where we just consider a lot of spheres, and the spheres want to go to the center, and they don't want to overlap with each other. So one of the challenges for agent-based models is when you have concrete things, they don't want to overlap. And we can model this, for example, with some kind of force which activates when things are getting too close to each other. So you could input that basically as a differential equation and just apply some solver. The main effort is basically to compute the sum. For each agent, for each I, you need to compute the sum over j. And of course, you want to do that quick. And that's very well known how to deal with that challenge. The video here doesn't show so well probably on the screen, but basically there's like 100 cells simulated on the GPU. And it needs like a few seconds to run. So, and this is possible because of the cell list method. The idea of the cell list method is very simple. You have your positions and you want to know what are the particles which are close by to each other. And what you do in this case is that you draw a circle around your particles with the radius where you're interested in. And then you only iterate over particles which are in these boxes around your position. So basically your task is have a lot of positions, put them into boxes, store the boxes somehow, and then be able to iterate over them quickly. And the code of using this with the package I developed is also pretty straightforward. So essentially if you want to use the package, all you need to do is you provide a vector of static vectors. For the positions, you provide a cutoff. And then you can construct such a hash grid. I will explain in a second. With the cutoff, you tell how many boxes do you want to have in total. That is like one of the parameters determining how quick the method is. And then when you want to iterate over the I and j's, you basically in the inner for loop, you can say, I only want to iterate over the neighbors within a certain cutoff radius. And this maybe gives you a few particles too much, so you should check the distance as well. This case, so this is how the package is used, and that's very similar to the more established package called cell list maps. So in comparison to cell list maps, some the features which I'm providing is that you can have unbounded domains, so you can have your points anywhere in space, and you don't need to say, oh, I'm in this area. And all of this is allocation free, what we see here. And I opted for a very minimal interface, so whenever you have some kind of applications where you need to quickly iterate over your neighbors, I think you can use this framework quite well. So spatial hashing is, for example, also used for collision detection or in rendering applications. So there are different setups where you maybe want to iterate over neighbors. So quickly about, okay, what exactly is the spatial hash? Why is it called hash? So the idea is, what is a very canonical idea is that the boxes, how do we store them? Let's say we want to store 6 boxes. Here in this example, then we could say, okay, we take a position, we convert it to a lattice position. So we just look into in which box am I at the moment. And then we say, okay, all the cells which are in the box number 1, I store in one list. And all the cells which are in box number 2, I store in another list. And you could periodically continue that. And that would be one approach, but for this approach, basically your lists would be distributed in a box. And sometimes when your particles are only in one area, that's not the best choice. This is where the hash comes into play. So instead of enumerating your boxes periodically with this kind of grid-like structure, you can also apply some random hash function. So meaning that here in the boxes get kind of like random numbers, and they're also not periodic, and then each particle which is in a box with a number 1, I store it in the same list. Each particle box number 2, I store it in the same list. And that's kind of a very nice approach to like have very fine control over how many lists do I want to have, and without determining how your domain exactly looks like. And here are the references for this. So it's used, for example, by NVIDIA Warp and other NVIDIA packages. Yeah, and okay, you can read this on the documentation, but basically you now have these two functions for the hash grid and the bounded grid. And one detail now is that if we want to use the GPU, we need to tell what data structure we want to use. And in the constructors, there's a fourth argument where you can tell I want to use a CUDA array with int 32s, for example. And that becomes important if we want to use the code on the GPU, because that should be a data type suitable for your platform. That can also be a metal array, or that could also be an any kind of abstract vector. And yeah, and don't forget sometimes to update the cells. So when your positions change, then you should update the grid accordingly. That's what the update function does. And now I want to show how to integrate that with on a GPU or possible other backends for kernel abstractions. So kernel abstractions is a really nice Julia package for developing platform agnostic code, parallel code. So you can target the CPU, you can target Intel 1, you can target M1, you can target NVIDIA, CUDA, and all these different platforms. So here I have the example with CUDA because my laptop has an NVIDIA GPU. So first you need to, in this case here we define the backend as the CUDA backend, and we need to decide what floating point numbers we want to use, so floating point 32. And then there is the package called adapt, which allows you to shift arrays onto the suitable format for a platform. So here, for example, we use adapt to shift the position array onto the GPU. And then finally, when we now construct a hash grid, the only thing we need to take care of is that we are inputting float 32s, and we input a CUDA array, and we use a CUDA array for the indices. And then writing a kernel in kernel abstractions is relatively straightforward. We just define a function with a kernel in front. And here we now need to take care that everything inside that function is basically static. And that is not really a problem. So the code is quite canonical. We have the index, we access our positions. And then we have the inner for loop over J where we iterate over the neighbors. And in some sense, you don't have to do much. And calling it is similarly simple. You just need to decide your backend, number of threads, and the length of your input arrays. And that's all. I would say the implementation here is quite canonical. It's just a parallel double for loop, and where we replace J over 1 to n with J over neighbors. And that's all. And the syntax allows you also to use it in different contexts. For example, if you want to use threads or some other backend or some other way to parallelize. So in particular, that means that this can also be used in agents.jl. I haven't finished implementing all the examples yet, unfortunately. But yeah, that was the idea of all of this. Okay, so a quick outlook on the alternatives. So there's cell list map, which is very established and sometimes actually faster. I will show benchmarks in a second. And there's nearest neighbors, which uses a different technique for that problem. And both of them don't work on the CPU, but they are both good for their applications. So I love both of these packages. The benchmarks here as follow. If you have uniform, like very dense particles with not many neighbors, then you can see how if we're here comparing basically the CPU serial performance to going to cell list map, we gain, and then using the package I implemented gains a little bit of extra performance, and we see that it doesn't matter if we use the bounded grid or the hash grid, both of them perform equally well. And then finally we can go to the GPU and gain extra performance. So that's basically good news for these applications. Actually, there are applications where the whole picture swaps around. So cell list map was developed with atomic simulations in mind, where you usually have a lot of neighbors. And in these cases, cell list maps is actually faster. So you need to consider what do you care about? Do you have a few neighbors or a lot of neighbors to pick the right package for your application? And what do I want to do next? So there are two big things. Like one is to integrate this into more examples or provide more examples how to use that for the models. So the videos I showed in the beginning, they're not open source at the moment. And then we need more sorting algorithms on GPUs, unfortunately, because at the moment that's also slowing down the implementation because it depends on sorting at some point. Okay, so I'm running out of time, but it's not really a problem. So the package bounded degree graphs is really simple. For agent-based models, you often have dynamic context between your agents. And I was always annoyed if I use the graphs package that I get allocations, and then if I want to hunt down allocations, somehow I never know, do I have allocations just because I'm creating or removing edges? And of course you can, if you know that there are a limited number of edges at each vertex, then you can just store them in a matrix, edges times how many neighbors do I allow at most. And this package implements this with the same syntax as graphs, so you can just use that type. I don't want to go into details, but basically you can provide metadata on the edges and on the vertices. And otherwise it's the same syntax as for graphs. So at the moment it's not implemented on the GPU, but yeah, in benchmarks I get like a little bit of performance increasement, but it's not like it's just ×2, and sometimes it's also less, to be honest. Okay, that's all about this. So in the end, I wanted to show a bit more mathematical pointers onto where I want to go next, to make more agent-based simulations on GPUs. And for me, one of the big questions is about contact mechanics, because agents pushing each other away leads to like very stiff problems, and that means you need somehow small time steps and all of these things which are coming with that. And don't worry about the mathematical formulas too much. I don't have the time to explain all of this, but there's a very nice theoretical series that instead of pushing your other agents away with some soft forces, you can actually make these forces super, super stiff, like infinitely stiff, and then simulate so-called non-smooth dynamical systems. And I have here some simulations where it shows this position-based dynamic method, which is really good for non-smooth systems, versus the penalty method. And the nice thing here is that the penalty method suffers from a lot of these issues, like let me make delta t larger. If we take a too large delta t, we have stiffness issues between our particles, and then usually the remedy would be to make delta t smaller, let's say. But that takes, of course, more computational effort. And if I go into the regime where the penalty approach really doesn't work, using the same delta t with this position-based dynamics method just works really nicely. And I think that's a nice method for a lot of agent-based models with things which should not overlap. And let me just show. So this method is not developed by me, but it was developed by NVIDIA researchers for all kinds of really cool simulations, like these simulations where we mathematicians are always jealous. And recently it was actually also applied for like elasticity equations by Anka Chen, called the vertex block descent method. And I think these methods would be really cool to have in Julia. So, and I think in the interest of time, I will skip a little bit over the mathematics here, but if you go to Gauss-Seidel, if you know the Gauss-Seidel method, it's nothing else than the Gauss-Seidel method. And you can do more mathematics, but I tried to implement differential inclusions or this framework as a package, but it's not so cool. I proved convergence for this method, so if you care about mathematical rigor, you can use it for agent-based models. And I also implemented like position-based dynamics for nice examples, like called learn GPU particles. And I would be really interested in using this method more in Julia, and for particle simulations, the really big problem is that you need graph coloring to apply it on the GPU. Because to apply the Gauss-Seidel method, you need somehow independent particles for which you can compute independently. So at the moment, what I would really like to do next is to implement a really fast graph coloring on GPUs, and I heard some people are also working on that. And I think that would further speed up these kind of particle simulations. Okay, so with that, I would like to stop, and thank you all for your attention.
Do you hear me properly? Yes, good.
Yes.
I have one brief comment, one question. But first, I just wanted to share my excitement. This is really nice and maybe useful for me particularly, so that'll be clear in the question. Comment just briefly. Sometimes you said agent-based models are where you go when you give up on doing a physics model. But of course, in some cases, and here I am biased, maybe they are appropriate exactly because you are modeling agents, like people or animals.
Yeah.
And my background is cognitive science, and we try to make models of single agents that are maybe cognitively or theoretically reasonable or probable. And we're developing software for doing cognitive modeling. So you take one agent and you put it in an experimental room and you fit the model to behavior to kind of check whether it's a good model of a single agent. And this is the question then. I was wondering how easy, or like, how customizable the agents.jl package is. Can I kind of come with my own functions from my own package that kind of define these various models and just plug them in? And would that also allow me then to simulate many of them in a space, which sometimes you do? Like, is that kind of modular?
I don't want to develop a package for agents. So there is already a package for agents in Julia, and like, of course, everyone who works on this is like, I want to make my own package, but it doesn't make sense. So,
but it integrates with agents.jl, right?
You can just use it with agents.jl inside the for loop when you compute your update. So there's nothing. It's just a normal Julia function in a sense.
Yeah. So as long as you have a function that decides how one agent moves, giving its environments, it is plug and play with your package.
Yeah.
That's really nice to hear. Okay, thank you.
Hi, yeah, thanks for the great talk. I wanted to ask, so you had mentioned that you did these agent-based simulations on the GPU, and one of the considerations was the grid-based position-based search, basically. And so when you did this on the GPU, basically, is my question, what all other considerations were there in getting this to work efficiently? And for example, does the entire thing run on the GPU, or do you sort of use the GPU for one step and then pull it back to the CPU, then GPU?
So not all the simulations I showed are on the GPU. I should make that more clear. So some of them are also just used on the CPU, and I actually struggle to find the right balance, because somehow the general wisdom is that you should sometimes do collision detection on the CPU in some settings and sometimes not. So I'm trying to learn the right balance. At the moment, my focus was just get everything done on the GPU and then see which part should actually be on the GPU or not. And
great, thanks.
Yeah.
Right. Coincidentally, the way we search for nearest neighbors in agents.jl is with a crude hash that you saw, crude cell list map. So you could actually do much better. You could actually replace our code with your much better code, perhaps internally, because we do exactly the same thing.
I didn't know that,
clearly
actually.
not as well. But
Yeah.
That's exactly also what we do. We have this nice cell. So
cool.
I'm looking forward to that.
Yeah, I would be happy. It's just 120 lines or something, so. Okay, thank you, everyone.
right. While they're setting up the computer, let me introduce our next speaker. Is Oscar from System in Marseille with his master student, Rim. They are specialized in high-dimensional statistics with application to health science. So today they're going to talk about how to develop Julia package to develop this relative survival analysis.
Not sure it works. The mic. Okay. Is it?
Thank you.
Did I did something wrong? Yes, I did something wrong. It's working. Okay, I hear myself. Thank you very much. As was just said, thank you very much. My name is Oscar Laverny. This is Rim Al-Ajal, and we are here to discuss an implementation that we did of some functionalities in survival analysis related to cancer datasets in the package netsurvival.jl. I'm going to do like that. So we'll start by an introduction to the field that we are going to discuss, and after that we'll do a bit of a comparison with what existed before. Spoiler alert, it was a bit of C code packaged into an OR interface. And we'll discuss a real data example to see and to show how the code can be used, and then we'll reach kind of a conclusion. So yeah, it's still me. I don't know if you are on the page in terms of survival analysis, but to give you a brief recap, survival analysis is a piece of statistics. It's a statistical theory that deals with positive random variables that are censored. By censored, we mean that there is another random variable that hides the one that we want. In the graph on the right, you have a few patients. Each of them has a lifetime that is denoted T, and some of them died, and we know that they died, and so there is a little cross at the end of the line. And some of them we lost to follow up. They could also be patients. It could also be that the study just stopped, and so these guys are still alive, or we don't know. But we still know that they survived up to this point, and we don't want to throw out the information. Because the time that we want to model is the time to death, to the real death. So these patients need to be handled a bit differently that standard statistics does, and this is the founding of survival analysis. This is a field that relies heavily on counting processes and local martingales analysis to get stochastics and asymptotics and stuff like that. Here we have a context that is a bit different than the standard one, which is what is called a relative survival context. And so it will be clearer if I describe the random variables that we are dealing with. There is E, the excess lifetime. It's supposed to be the lifetime of the person with respect to the disease that we are studying, in particular some cancer. There is P, which is a population lifetime. It's supposed to be the lifetime of the person with respect to other causes of mortality. And so the patient can die from one or from the other that are supposed to be independent. The two risks are supposed to be independent. And I denoted O, the overall lifetime, which is just the minimum between the two. And then there is the standard censoring things. So you have C, a censoring time, that is another independent time. T, which is the minimum between O and C, is the time that we will observe. All the rest is not observed. And we will observe an information that tells us, as did the cross and the circles on the graph before, that the observation is censored or not. But the particularity in the field is that we do not know if the patients that we have actually died from the cancer or from something else. This is an information that is really hard to get from doctors and from cancer registries. Even if we want to model the risk with respect to the excess lifetime, we want to model the distribution of E and not the distribution of P. So everything else is just nuisance, and we want to get to the distribution of the random variable E. Since this cause of death indicatrix is not available in our data sets, standard survival analysis that I described right before is not applicable, and we need to do something smarter. So in terms of notations, we'll use S to denote the survival function of a random variable. We'll use lambda, the big lambda, to denote the hazard function of a random variable, which is just minus the log of S. And the small lambdas, or d lambda, to denote the instantaneous hazard, which is in terms of positive random variable on the positive part of the real line, which is our case here, quantities that characterize these distributions. Our goal, I just said it, is to estimate the distribution of E, let's say by its hazard. And for that, we have a few assumptions on the joint distribution of all these random variables. The few assumptions are that they are mostly independent from each other. The several causes of death are independent from each other. And there is one, the population mortality, that depends on a few covariates. And we use this covariate to describe the fact that an older man of age 82 doesn't have the same mortality risk as someone of age 42. Even if they have exactly the same cancer, they don't have the same mortality with respect to the population part. And so the distribution of P varies from individuals to individuals, but not the distribution of E with respect to the cancer. In the computations, we will need to access the distribution of PIs, the population mortalities, which are extracted from standard life tables produced by the statistical offices in each countries. And in particular, it's instantaneous hazard, lambda PI, and all the code with respect to these rate tables was actually moved to another package because it's useful in other places of the infrastructure. And so it's moved to the ratetable.jl package. You go.
Given the relative survival context, we're going to introduce the standard estimators in the field. So when we're talking about the estimation of net survival, we are mainly talking about estimating the instantaneous or cumulative excess hazard. And for that, there are many methods that exist, but we're going to mainly be focusing on PowerPerme, which was introduced in 2012 and is mainly used in research. And when we're talking about net survival, people usually use this method. So it uses the inverse probability weighting. Here we're referring to the populational survival function. And the estimator is given by the formula on the slide. And the variance is estimated using the same weighting. And one good thing about this estimator is that it's biased but convergent and asymptotically unbiased. And what's really cool about Julia when coding this is that the code resembles the formula because we're using the same notations. And so when someone is going to read our function, they're going to understand exactly what it does as it resembles exactly the mathematical formula presented. One more cool thing is that in this function, 60% of the runtime is due to the exponential function, which is unavoidable, meaning that it's very thoroughly optimized. And now that we have our net survival functions, we want to be able to compare the net survival functions between groups. And so this is where we introduce the logrank test, the Crafeo logrank test, and where the null hypothesis aims to compare the excess hazards across partitions inside of a group. And to be able to do that, we first construct the z vector, which is the difference between the uncensored death process and its estimation under the null hypothesis. And from this, we're able to construct the test statistic under the chi-squared distribution under the null hypothesis, where the variance matrix is also given by the estimation in the slide. The null hypothesis is rejected when the p-value calculated is under a certain an error margin that is chosen by the researcher. Given the survival rates, it's also important to be able to separate it by cause. Here we did the crude mortality, which allows us to calculate the mortality rates separated by cause. So we have the mortality rate due to the certain disease studied and the mortality rate for the population. And the observed rate is going to be the addition of the two. So here it's with respect to the excess hazard, and this is with respect to the populational hazard. And to estimate this quantity, we're going to be using the Cronin-Feuer estimator, which estimates the observed survival function using Kaplan-Meier, and the excess hazard using one of the methods. Usually it's Power-Permet, but there are other methods. That are there are two that are also included in the package, but we are not going to be presenting them. And lastly, an important functionality in the package is the Nessie function, which allows us to estimate the sample size in yearly intervals, and it's given by the sum of the populational survival function. And the expected lifespan as well, so how many years left are on average for a certain group of people, which is given by the constants of the hazard rates in the mortality tables. This is implemented in the rate tables package that was constructed complementary to the net survival package, because we saw a need to have an independent package that deals with rate tables as well. And it relies also on the expectation function from the distributions package.
We wanted to give you in a few screenshots a comparison with the OR and C++ code. It's actually C code that was in the original version. If you look at the crude mortality estimator that we just introduced, you'll see that basically it's 3 lines of code, right? It's 1 comprod and 2 comsams. So it's not really complicated. But if you go to the OR package, yeah, here you have the Nessie function, which is also very small. If you go to the OR code, then the number of lines goes crazy, and the code is mostly unreadable. It's not always commented in English. Comments are mostly wrong. Yeah, it was a pain. And at the end, yeah, the C code is even worse. And at the end, we were able to reach a size of code that is about 15 times as small, while having the same functionality and increased readability. The code that we produced includes unit tests. It includes documentation that is readable in English with proper descriptions of what's happening in it, and we can actually trust the implementation that we made, while the original one is harder to trust. And on top of the cake, if I can speak like that, it's the time multiplier, which goes a bit crazy, and so we have a runtimes that are about 20 to 30 times as fast, depending on the functions that you are using with respect to the original OR version, which is good if you consider that computing 1 survival curve used to take about 2 seconds. It goes down to about 0.1 second. If you have 1 or 2 to compute, it's not a big deal if they take 2 seconds. But if you compute thousands in the middle of more complicated algorithms, then it can add up quite quickly. Most of the win in terms of time is due to carefully thinking the infrastructure and the classes, and in particular the rate tables, the tables in which hazard rates for the population mortality are given with respect to the age and the date and the countries of the patients. These tables were implemented in a horrible C code. And here basically this function just fetches a value in a matrix. And on this function we won crazy.
Having explained the functionalities of the package, we're going to present an example that shows you how you can use them and how you can interpret them. For this reason, we're going to be using the coloREC dataset, which is a rather small, basic dataset. It has around 6,000 patients that are diagnosed with colon or rectal cancer between 1994 and 2000. It has 7 variables. Age, year, and sex are going to be used to be able to get the populational hazard rates. And status for censorship, follow time, or survival time as well. Cancer stage, that takes the values 1, 2, 3, or 99 for unidentified. And cancer site, so colon or rectal cancer. And it's sourced from the Slovenian Cancer Registry. For this reason, we're going to be using the Slovenian population mortality rate. So we can extract the populational hazard rates. The first step in any data analysis study is to look at the distribution of our variables. So we're going to look at the age and the follow-up time. And as we can see that most of our patients are aged between 60 and 80 years old. And as for the follow-up time, it takes a quick dip rather quickly. And we can tell that at around the 5-year mark, we've lost a lot of patients. Given these information, we're going to apply the PowerPoint estimator, which uses this interface. It's also very similar to the R interface, so if anyone is used to the R interface, they can quickly adapt to the Julia one. And the one here can also be changed to any of the variables. That way we can get different tables. So let's say we include the variable sex. We can have a table for the male patients and another table with the female patients with the net survival estimator for these patients. And the table is given in daily intervals. It gives us back the confidence intervals, the variance, as well as the excess hazard and the survival and the excess estimated survival function. When putting the results in a graph, we get the first graph on the left, which is a little abnormal. But this is the same in R. It's not an issue from the code. It's just an issue with the data. We get large confidence intervals and also the probability, the survival probability that increases, which is not normal. But it's mainly due to the fact, actually we're going to explain that in a bit later. And when zooming in on the first 5 years, we get a more normal looking survival function that also quickly falls under 50% within the first 5 years. Let's look at the loss of accuracy, which is represented by the large confidence intervals. And for that, we're going to be looking at the Nessie function that allows us to estimate the sample size throughout the study, as well as the estimated lifespan. So when looking at the estimated, the expected sample size, we get that at the end of the study, we've lost almost 3,000 older patients. Here we defined the older patients as older than 65 and the younger patients as younger than 65. So we've lost more than 3,000 patients, older patients, and less than 1,000 for the younger patients. When you're losing this many patients, by the end of the study, you're getting a loss of accuracy because you don't have as much data as you should have to be able to estimate. And this is especially shown in the graph in the slide, where the slope for the older patients is much harsher than the one for the younger patients. And we can tell that at the beginning of the study, we had a lot of patients compared to at the end of the study. And as for the expected lifetime, or the years left for each of these groups, we have on average 14 years more for the younger patients, which is logical, but also it also means that at around 10 years, we've lost almost all of our older patients, a good majority at the very least. We can also cut at 10 years instead of 5, because we decided to cut at 5 when drawing this graph on the right. We can decide also to cut on the 10-year mark, but we decided on 5 because at the 10-year mark, we've already also lost a lot of patients. When running the crude mortality function, it's also interface-wise, it's very easy. You just apply the power per May estimator that we applied at the beginning. And at the 5-year mark, we can tell that out of the 64% of the patients that have died, 53% is due to the colon or rectal cancer, and 11% is due to other causes, which also helps justify the fact that we cut at 5 years, because we still have a lot of patients dying from the cancer and not from other causes. Lastly, we apply the Graphéo test to be able to compare the net survival functions between groups. And we found that only 2 variables are important in the study, which are the age, so younger and older patients, and the stage, because they both gave us p-values that are very, very small, and so they're necessarily very significant in the study. So in conclusion, the older and the more advanced the cancer stages, the lower the risk of survival, which is a very logical conclusion, which is why I said it's a very basic example, but it was mostly to show how you can use it and how you can interpret the results.
A small note before reaching the end. All this work is started only for the net survival case, but then we understood and we saw the infrastructure, and we are trying to build a bit more. And so there is this JuliaServe organization that was constructed to hold this work, but also infrastructure, and there are a lot of projects in it around survival modeling in more general terms in Julia. There will be more in the near future on this front.
So again, to summarize, survival analysis uses censored data, and the variable of interest is the time of survival. With specific cases, we have the cause of death that is unavailable or unreliable, which is why the relative survival field was born. To be able to handle such scenarios. Our Julia implementation is much faster, more concise, easier to read than ours, and making it future-proof. The JuliaServe organization has hopefully a very bright future ahead, and any and all contributions are more than welcome. Thank you.
Thank you very much.
Oh, and if there are any questions, go ahead.
Any questions?
Hey, thank you so much for the excellent talk. I had a question on slide 18. You're showing the code where you could have the exponent syntax. Yes, the exponent syntax where you're saying you could, for example, change out age 65, have like different variables in the formula function there. I was curious, how well does the package right now handle intersectional populations? Say if I wanted to look at maybe age 65 as well as maybe by gender as well. Is the package right now capable of this intersectional analysis, or where is it at right now?
Yeah, we can actually, it groups people, so I don't, hopefully I understood the question right. Yeah. So if you want like age 65 and female, age 65 and male, that can also be a possibility. You just add sex plus age, and it would group them in that order.
Okay, thank you so much.
Any other questions?
Thanks. And actually, on the prior slide, I had another question. I was curious when it came to slide 17. Okay. Yeah. I was curious when you calculated follow-up time. How did you calculate follow-up time? Was that part of the net survival package itself, or did you have to do that manually, or what was the process?
The follow-up time is it's data in the cohort. So when you're dealing with a data set that is used for net survival or survival analysis, usually it includes the censorship and the survival time. These are variables included in the data set. So it's not calculated, it's just the data.
Just a given.
Yeah.
Okay.
The follow-up time is T in this slide. The follow-up time is just T on this slide. It's part of the data set.
Okay, thank you.
Any other questions? If no questions, there.
Is there another kind of system or data set that you can use to sort of validate your findings with more sort of high throughput? Because obviously, like, cancer patients are very heterogeneous. The reason why they're in clinical studies is because they're dying anyway, and they're trying to, it's a last resort, right? So comparing patient to patient, it's you have to take into account what prior therapies they've had and all that kind of stuff. Is there maybe like another kind of data set that you can use in nature that's perhaps cleaner and easier to access?
No.
No.
The problem is that the data sets on cancer patients is rare, and to be able to pool cancer patients from several countries and several places, we are obligated to go through these methodologies. The cause of death is of course unattainable. There are other information in national databases, but when they are pulled in the global cancer registries, those are usually not available at all, and you get very few information about the patients themselves. You might get sometimes information about what they got treated with, and so you can use it as a covariate to check if the net survival of cancer patients that did had some treatment is better than others, to validate the treatment itself. That is one of the potential applications of this work.
Are there no equivalent model like databases for mice, for example?
For
mice?
For what?
I think what your question is basically asking if we can apply it to other than cancer data sets. Is that?
Yeah, or whether there's any advantage in finding other data sets that have like more data points and are more readily available than cancer. And
Well, I think mainly survival analysis in the first place can be used for things that are even outside of life sciences. You can use it well, the most important thing here is that we're the main star, or like the interest when doing an analysis, whether it's relative survival or just survival, it's the time of death. So whether we're calculating it because of cancer or for other reasons, it can be done. It's just more of a researchers that are going to be using this tool that are going to be exploring other data sets more than us as statisticians.
The net survival stuff is really for those kind of cancer registries where the number of lines is also limited, because the number of persons that do get colorectal cancer is not infinite. But there are on other survival issues, even in the medical context, data sets that are way larger, but not in the net survival context. And there is this survival models.gl that is upcoming that will probably do stuff to answer some of these questions, to build more strong models, right?
Thank you.
All right, so maybe if no other questions, I have one last question. So it's probably like it's more common when you see a statistical analysis is written in R, right? So when you transit from R to Julia, what are the challenges you encounter?
As someone who's going to be using the package, or as someone who
Developer.
Well, the first 2 weeks when we were starting this project, we were looking at the R code, and it was really horrible to look at. It was really hard to read. And so we mainly decided to give up on looking at the original source code, and we just looked at the math part and decided to apply the math logic instead of the R logic, because the R had not a lot of logic, in our opinion.
Okay, great. Thanks. Yeah.
You're welcome.
Let's give a round of applause for Oscar and Rim. Yeah, it should be there. Our next speaker is Peter from Aarhus University and the University College London. So he's specialized in computational modeling applied to psychology and neuroscience. So today he will tell us how to use Julia.
So I just go on the website? Like it didn't. I do, but I don't. I can use this dongle. I'll be quick. Yeah, I have USB-C, so that works.
All right, let's welcome Peter.
Okay, you can hear me? Hi, I'm Peter, a PhD student from Aarhus, Denmark, doing cognitive modeling. And I'll present 2 packages for that, one for cognitive modeling general, and then one for a specific model type called the hierarchical Gaussian filter that we're building. That I hope will integrate well with stuff like agents.jl, Turing, GLM, etc. But you'll see that in a second. So I'll start with just introducing what cognitive modeling is and how that relates to something like agent-based modeling and computational psychiatry, and describe the package called action models, which is in general for that purpose. Then I'll just describe the hierarchical Gaussian filter, which is a specific type of broadly applicable model, and describe the package for that. It's quite a bit to go through. We'll see if I get all of it, otherwise it'll be a bit fast in the end. If there's clarificatory questions, do ask them on the way, but otherwise there'll be time in the end. Okay, so cognitive modeling is a method used primarily in cognitive science, also in computational neuroscience, computational psychiatry, but all coming from the attempt to reverse engineer the mind. So figure out what are the processes that create behavior. That's how we understand mind or cognition. So that's consciousness is a different question. For now, we're just at functions that make us do stuff. And coming out of psychology, but being scared of a big replicability crisis, cognitive science has really embraced the natural sciences as an attempt at a salvation from that. So that means experiments, it means statistics, and most importantly, it means computational modeling of minds. Computational modeling is a very standard technique in many places, like physics, biology, etc., where really what you're doing is you have some stuff you can observe, maybe some light. You have some stuff you can't observe directly, maybe molecules in the sun, but it could be many other things. And you build a model, also called a generative model, of how molecules in the sun might change or look like, but also importantly how they generate or create the things you can observe. So you have a causality one way, and then you use some kind of inference to figure out what must be the case for the things you can't observe. Often we use Bayesian inference, which I'll get to in a second. Of course, we're not modeling stars, we're not modeling cells, we're modeling people or cognition. How does that look like? Exactly the same. Except that we have some stuff we can observe, that's behavior. And that's usually what people do. Actions, sometimes they're called responses, decisions, outputs in general. And we also have what people see, so their observations, the stimulus, or their input. This we have access to, often because we create a little experiment where we design this and look at what people do. But also more generally, we might look at what people do out in the wild, etc. And then we have some theories about some kinds of processes. This is a very old school cogsci theory about working memory, but it's not so important. What's important is that that should create the actions given the observations. If we make a computational model of this, we can do exactly the same methods and try to make inferences about these unobservable mental phenomena based on what people do. We can conceptualize this like this. So we have, again, this is very simple and even a bit ugly, but we have some inputs, we have some actions, then we have some mental states that change over time. This might be how surprised you are, your current belief about the thing you're looking at, etc. And then we have some parameters, maybe your learning rate, which is how quick your beliefs change. And all that the model is how, it's basically everything inside these boxes, so how your inputs affect your mental states. Maybe you get zapped and you start to form a belief that pressing this button will zap you. And how that in turn affects your actions, so you stop pressing the button, depending on some parameters. And then basically all you want to do from there is either simulate what kind of actions would people do if they had some types of parameters in some situations. Or you want to ask, I have some people here in an experiment, I have their actions and their inputs, now I want to find out what parameters did they have, what kind of learning rates did they have, for example. Often the question is, let's say you have people with and without schizophrenia, and you want to find differences in the types of mental states and parameters that define them. We do this with Bayesian parameter estimation, also called model fitting. You know, not to spend too much time on that, but you come in with a prior for what the parameters might be. You have your evidence, which is just the behavior, and you estimate, make a posterior estimate for what the parameters probably were given your priors and the data. And the gold standard in the field is to do sampling methods, MCMC, which I won't talk much about here, except to say that until now, usually people have done this in STEM. STEM is nice and beautiful, but it is technically hard to use, particularly because it's a separate language. Often people work in R, and then they also write their models in STEM. That makes it inaccessible. It means that it's only the technical people who ever do cognitive modeling. The rest would stick with linear regressions on their experiments. Of course, Turing can do this too, and it can solve the two-language problem, and that makes it really easy to write your models. And the attempt here is to make a package that can make that plug and play for the parameter estimation, etc. Even to combine it with linear regression. Cognitive models, there are many kinds. So there's a whole species of models from mathematical psychology. Some people might know reinforcement learning models. Some of these control models. I do predictive processing models. There's the ACT-R cognitive architecture models from the 80s. Some people consider a neural network a model of cognition. Others just consider it a machine learning tool. I'll talk a little bit about this one. The rest is a whole world. But like a simple example would be the Rescola-Wagner, where you have some value expected with maybe taking a choice, and you get an observation, and you just take the difference, the prediction error, have some learning rate, and you update it. And if this is 1, you always update it to the thing you just observed. If it's lower, you update a bit slower, so you're hesitant. And then you have some action that depends probabilistically on this expected value. This case is a continuous action, but it could also be binary one. It's one of the simplest canonical cognitive models. People use it exactly in these experiments where you make people press buttons and they get money or they get zapped or whatever, and they start doing the thing that gives them rewards more. And like I said, fundamentally it's to make models of mental mechanisms. People use it in computational psychiatry to try and figure out what's going on when people have schizophrenia or addiction. You can use this for agent-based simulations if you want to. There's something called cognitively informed agent-based simulations where you take people in, you fit models to them, you get models of people's behavior that's data validated, and then you plug that into an agent-based model afterwards, instead of just making up simple rules. And some people also try to use some of these models, cognitive models, for making agents, artificial agents, whether they're robots or something else. Okay. Action models tries to make this easy, so that basically we want to abstract away as much as possible of the technical bits, so that the psychologists from down the street who you're collaborating with can also use the package, while making it flexible enough to do whatever you need it to do. So we've called this agent. Given that there's agents.jl, we might have to change its name. I'll find out. But for now, an agent, because what is an agent? It's something that takes inputs and makes outputs. Action model, a model of the actions you take. People just need to make a function. This is an example of the Rescola-Wagner, but really just a function that takes an input and returns a distribution for the output it should do. And in this case, we have the Rescola-Wagner here. We have an interface for storing parameters inside this agent object and updating them and returning them. This is as easy as we could make it to just make literally a function that takes an input and returns an output. Then you just need to make sure to tell the, in addition to this model, also give it the parameters and the states, so the things that don't change and the things that can change over time. Maybe we made room for extra settings because sometimes that's useful. Things that are not estimated, for example. And you create this agent object. And we're making a library of standard models so people can use them. That's often the case. People just want to use this model they know of already, and it's fairly easy to build this library as you go. Once you have them, you can simulate behavior, so you can either predefine some inputs or you can put them in a loop and get them based on what people do. And we have these functions where you give the inputs to the agent and out comes actions. And also it simulates, let's say, trajectories of prediction errors or changing beliefs, and you can extract them and plot them. And we have some plotting functions that will let you do that. And in this case, very simple inputs. You have a Rescola-Wagner reinforcement learning that updates its expectation based on what it's seeing. Its learning rate is not 1, so it's hesitating a little bit. And it would not be hard to put this in agents.jl if you want many of them walking around. But more importantly, we also want to be able to fit it to data. And all you need for that is you need some priors, in this case also dictionary, although we're looking at optimization. You need some data, which is just a set of inputs and actions. And we have just for the psychologist down the street, just one function. Just makes this into a Turing model and runs it. But you can also extract the Turing model and do whatever you want with that from there. So this just returns that. And having, you put in the settings as usual there. And notably, we can also do it with a data frame where you just have inputs and actions. You can have multiple of each for each time step, and then you can have multiple participants in experiment and fit the whole thing and parallelize it. And plot it, and these are of course Turing's normal plots, and we have some extra plots as well where you look at the prior and posterior next to each other. Yes. Yeah, you just need to specify which columns are what for it to run. The hope is to get something that looks as close to something like BRMS, for people who know that. We just do linear regressions, but Bayesian, but for cognitive modeling. Finally, some extensions. So for example, we're just working on now on being able to add a Turing GLM formula where you just say, by the way, I think the learning rate in my Riskola-Wagner depends on age in the dataset, if that's it, or you just put in a linear regression. You can fit it all in one, which is the gold standard, but usually only accessible to the most technically strong users of these things. We're working on a neat interface with RVs, which allows many of these standard analyses and so on. And of course, sometimes you have complex models that you don't want to just be in a dictionary, but we have packages that allow you to build those kinds. And these are two kinds, active inference models, hierarchical Gaussian filters. I'll talk about this one. The point is you can easily make a package that relies on action models. And if you make it compatible with that, you get all of the fitting for free. Okay, what's the hierarchical Gaussian filter? It's a specific type of model which is called a predictive processing model. So just say what is that general paradigm, and then I'll say the specific model. In predictive processing, you combine basically three things. The Bayesian mind hypothesis, where you hypothesize that what the mind or the brain is really doing is doing Bayesian inference to make guesses about what's going on outside in the world. And then those guesses or inferences about the world inform your actions. And your experience is the hypothesis also. So something like when I experience a lot of chairs, it's because my brain is guessing that there must be chairs, depending on or based on the inputs it gets. Note, funnily enough, that by taking this hypothesis, we are using Bayesian inference to model a system that is also doing Bayesian inference to model its environment. It sometimes gets a bit hairy. It's called meta-Bayesian approach, or observing the observer, or modeling the modeler. So now we'll kind of go into the perspective of the agent, which is also doing Bayesian inference. Notably, usually in these theories, you assume that the mind is not doing sampling, because it takes too long. And for other reasons, there are some principled reasons too, but doing variational inference, which is faster, less accurate, but faster. And that's a whole other discussion. And finally, we rely on some of these predictive coding theories, that's brain theories, suggesting that brain sends predictions down, gets errors, and sends the errors back up and updates the predictions again. And it turns out that predictive coding and variational inference become equivalent under some assumptions. So they kind of combine all of these into this predictive processing framework where you say the brain is doing Bayesian inference on the environment, specifically variational Bayesian inference, implemented as prediction errors being sent up and down. And importantly, the main function of the brain or the mind is to minimize prediction errors. You can minimize prediction errors in two ways. One is to change your predictions so they fit the world. Another is to fit the world so that change the world so that it fits your predictions, also called action. It's a whole field. Some people think it's nice, some others do not. But I think the main promise of that approach is that it's a general framework you could use for most of cognition in general. So whether it's memory, that's thought of as a, let's say, a post-diction, a prediction about what happened in the past. You can put in preferences as unchangeable predictions that then you have to act and make them come true in order to minimize prediction errors. You have learning, inference come very neatly out of this. It seems to generalize most of the reinforcement learning methods and the control methods, etc. So one can be very ambitious or one can be very relaxed about the paradigm, but here you go. Importantly, once you have this, you already have decided what's the loss function, what's the kind of main processes that a predictive processing agent does. The only thing you don't get for free is what is the agent's model of the environment like. And that's then becomes the main task of the scientist. I assume he's doing Bayesian inference, but I don't know what his generative model of the environment is. Now I'll have to try and find out. The hierarchical Gaussian filter then is one type of generative model an agent might have of the environment. Importantly, it's a very broadly applicable generative model that works whenever you have continuous states that you don't know how they change, but you do know that they change, which some would argue is most of the time. So some people are calling these types of models universal generative models because they apply more or less anywhere as long as you don't have a better, more specific knowledge of the types of dynamics of the environment. And so that's one argument for why the mind or the brain might do this. You know, something is changing, I'll do this. What are we doing? Actually something very simple. We're assuming a Gaussian random walk of some continuous state in the environment. They look like this, right? So you start, you go randomly, so on every time step you sample a new position from a Gaussian centered around the position you're currently at. You jump around. Most of the time you'll kind of go something like this, but sometimes you'll go outwards. A Gaussian random walk is described by two parameters, a volatility and a drift, omega and rho. Volatility is the width of the Gaussian, so that's high volatility you would go up here or down here, low volatility you would stay in here. And drift you would have a linear drift that can go up like that, so you can have a direction on it too. And importantly, since we assume that the agent assumes a Gaussian random walk of the environment, these two parameters becomes the agent's assumption about the environment. We can learn them, I'll get to that, but for now they're just parameters. So what we are trying to infer is what the agent assumes about the environment. How volatile does this person think the environment is? That has lots of implications, you know, etc. People who have grown up in volatile environments later on assume that things are changing or that you can't necessarily trust what people are saying, etc. So you have these kinds of interpretations, but also a volatility assumption translates directly into a learning rate. So that's why I can generalize some of these learning rate-based models. We can draw it like this. So we have, this is the agent's model of the environment. Some continuous state, we might call it x. It has these two parameters and it's changing. And on every time step, so these are discrete time models, we get an observation, u. That observation is drawn from a Gaussian, centered on the real state, but so there's some noise. So I have Gaussian noisy observations and the environment is changing. This thing in the environment could be someone's position if they're moving. It could be the probability that something will happen. It could be what I think you think of me. You know, there can be many kinds of things. And note that this is actually exactly a Kalman filter. When you're assuming a random walk in the environment, you get noise observations, you're doing inference over it. The hierarchical Gaussian filter then nodalizes this and lets you build structures of many states that depend on each other. That's why it becomes very broadly applicable. So the most standard one is you assume what's called a volatility parent, saying there's another state in the environment that controls the volatility of the state. That's useful if you're in a place where the volatility of the environment is changing and you have to learn it. So now it's stable and I have to up my learning rate if the environment is stable, but when it becomes unstable, I now, because I have a state in my generative model, can learn that the environment is unstable and I'll lower my learning rate. It might look something like this. So let's say I get some, this happens to be the exchange rate between dollars and Swiss francs. I get some inputs. The red line is my filter or my inference about what made these inputs, given some noise. And then I'm also learning the volatility. And we see here when it changes fast, we up the volatility and we lower the learning rate. This is the classic hierarchical Gaussian filter. It's just a generalization of the Kalman filter that's also volatility sensitive. And that's justified in these predictive coding theories. Good. There are many ways to extend this. You might have two observations of the same state with different noises, perhaps. You can also learn the noises, maybe even separately of each of these. So maybe you have two modalities and one is noisy, one is not. But the noises are changing, so we'll learn them both. You can have binary states that happen with some probability, and we're learning that probability, and maybe that's also changing. So we have a volatility parent on that, you know, and so we get binary observations, and we're learning the probability of getting them. We can even have combinations. We might have categorical states where you have X categories and you're learning the probabilities of them. Or state transition models where you're not just having categorical states but transitions between categorical things. And we can, in general, build and grow these as we want. Making it a broadly applicable model. And of course, these are just inference paths, so they don't generate any actions, and that means we can't actually fit them to behavior, so you need to add a response model. That is just given my belief about the environment, what do I do? And usually they're very simple, because often experiments are simple where you just have to guess what's going to happen next, but they can be more complicated. I won't go into details with those. So the package then makes it easy to do this, which would otherwise be difficult, because usually if you're doing predictive processing models, you have to derive how to do variational inference over that model by hand, which few people can do, and that means that they're not used in practice. But because it's nodalized, you don't need to do that, because all of the updates are local per node, just given their parents and their children. So all you need to do is you need a list of nodes, in this case these 3. You can put in some specifications here or later. Put in a list of edges, depending on whether it's a volatility parent or what's called a value parent, if it's the mean that they control. And we're actually going to move beyond just Gaussian random walks and have also stationary distributions of any exponential family, which is nice. And of course, this I realize could be done with maybe graphs.jl, so that's one way to extend it, also for nice plotting stuff, and etc., or other analyses of it. You create an HGF, and there you go. Of course, there's a list of pre-made HGFs, like basically all the ones I just showed are already in the library, and it's growing as we're adding new ones. And we're making a little drag and drop editor where you can make them yourself. Then you add a response model. In this case, we take an input, we update the HGF with the input, and here I'm saving the HGF in, we call it a substruct, which is just a place where you can put some struct of your own choosing in the action models, which dispatches on the functions. So you update the HGF, you take out some of its states, in this case the posterior mean, so the belief about what the position is. And then you just, in this case, take a Gaussian noise on your belief about the state and returns that as your action. So this works in experiments where you just have to report what you think happened. But you can do other things here if you want, and because it's modular, this allows that to be a bit easier. Much of this stuff was usually in MATLAB and hard to read and annoying to edit and impossible to fit as well. You can create an agent just like before. You just add the HGF as the substruct, and there's premates for them too. And then basically you're in action models territory, and you can do all the functions you had for action models, like fitting them, plotting, etc., from there. And getting nice little parameter estimates for the different parameters here. So it would be nice to take something like complex HGF, in one line of code, do linear regression multi-level on top of a complex cognitive model with a full data set nicely parallelized, but make it easy for the psychologist next door. And you can extract then these belief trajectories, and that are often used for neuroscience. So where you basically take out, let's say, the prediction errors of the beliefs, and you regress them on brain data to find out what areas of the brain are related to this kind of beliefs, for example. Or some of these DCM models that do it a bit more deliberately, also with a generative model. But of course, Julia has packages for these things, and it would be nice to make them interface there too. We haven't done that yet, though. But it's easy to get out a time series of beliefs, and yeah. All right, I think I am out of time, but I also think that was a brief run through of these two packages. Thank you.
Thank you. Any question for Peter? Yeah. First you, and then we will go.
Hi, nice talk. Can you apply this to psychophysical experiments? What happens when you have not enough data? Because I understand with EEG or something you can get more data, but what happens for when you have scarcity of data?
Let's say when it's expensive to actually get in participants, for example, in psychiatry situations. I mean, we're doing Bayesian inference, which, as far as I know, is the best way to use the data, at least. And once the regression part is up and running, we can do random effects, which is the same as hierarchical models, which is the gold standard. But that doesn't save you, of course, from having little or bad data. Yes, so I think we'll, as far as I know, this would do the best that I know there is, right? But exactly right. And of course, to use imaging data for the cognitive inference, you also need a good theory of how exactly your imaging data relates to the changing beliefs, and that's completely unsolved, I think. Yeah. Yeah, does that answer that? Yeah, unfortunately. I mean, that's a whole other field, right? Can we use apps to collect data? And yeah, exactly. Yeah.
Sorry. Thanks again for the nice talk. I'm one of the robotics guys who thinks about using cognitive models. And so what is a typical experiment? Or you said that there are experiments, but you did not show some results of bigger experiments. So what are typical experiments where you could show results? What can be done, and what shall be done in order to infer something like motivation or something? If you bring a robot and a human together, is it possible at all?
So my background is not robotics, which means and the problem, this field comes out of not robotics, which means it's often experiments with discrete actions given some input that's not actually that useful in itself for moving robots. Also, this package is optimized for parameter inference, cognitive modeling, less than robotics. There are some of these cool packages, may have heard of RX Infer or something, that uses some of these same models, but has a much more, as I understand it, engineering-minded approach that optimizes for speed and so on much more. But what kind of experiment? I mean, we're using the software for a few projects now. For example, one big one is where they have an experiment where you condition people to hallucinate. So you play them sounds, you show them images. They have to press a button whenever they see the image or hear the sound. It's two different, let's say, sub-experiments. And you make it so that some sounds usually come with some images, so they get used to this. But then you give them really noisy images and sounds, so that sometimes they'll press the button without it being there, and you take that as a hallucination. I'm doing the analysis for this experiment, but I didn't collect it. And then you find out that people with schizophrenia hallucinate more often. You fit a model, and it looks like it's because they rely more on the priors.
Okay.
That would be one kind of story you can tell with this. But I realized that's not that useful for robotics. Something like these active inference models are maybe more useful there and in other implementations.
Okay, thanks.
Thank you. I hope that's useful.
Any other questions?
Then, thank you. I also speak softly. Okay. And famously. Okay. So I'm sorry about that.
No, it's okay.
Was it hard to
I wasn't
hear?
sure if your mic was off. I didn't want to.
Thanks for the talk. It's really nice. I'm working on the same field, but more or less I'm actually the one giving
But because maybe, do you have a sound from here? Because I bring my Bluetooth speaker anyway. I can use my Bluetooth speaker, so maybe it's easy.
No, I prefer or the HDMI for the sound, or I have a separate sound card because we're streaming, so Bluetooth speaker is not going to the stream.
Oh, okay. But then I have to try if I can, because I have to set the output of the audio to if this works.
Yeah, if you need help, then
okay.
maybe you can help if there is a...
Okay.
Yeah. Okay, thanks.
Because I need to tell port audio to use that.
But you only have audio, or you have a presentation presentation where there's a
no,
small
there's
movie
no
or
audio in the presentation. It's
This is the track that's for me. So are you going today? The next one. Is it cognitive modeler too? Yeah. So I guess you, if you want, would have to put labels on it. It sounds like you do more models of neural behavior.
Yeah, but we try to do both at the same time. And using the same model. Neural data also have to be really small to fit the media.
That
is
is
joined. Usually have to trade off. So usually rather than behavior.
All right, let's start our next session. It's again on biological science. Our next speaker is Ahmed from Donder Institute of Brain Cognition and Behavior. I believe he's in Amsterdam.
Nijmegen.
Nijmegen.
Yeah.
Okay, great. All right, he's going to talk, tell us how to use Julia to do neurodynamics.
Okay. Yeah. Yeah. Thanks. So yeah, what I want to tell you is more about this Julia package that we're building or actually releasing. But I want to try to a bit more to motivate why did we want to build this and what's the research question that we're trying to answer in the first place. So basically, I think if you attended the previous talk, I think the main problem is that we have no idea how the brain works. We kind of know, at least on a biophysical level, how a single neuron works, and we can explain why do we see these kind of observations, when does a neuron fire and when it does not, but we don't really know how does this translate to what we observe, to our daily behavior. It's not like we have some statistical framework to take us from micro observation to macro observation, like in statistical physics or something. But in recent years, there has been a lot of success, or getting a bit closer in trying to recognize the brain as a dynamical system, and mostly looking at not just single neurons, but multiple neurons. Now with advancement in neuroimaging, we can look at multiple neurons at the same time, and we can do these kind of cognitive experiments and try to use this dynamical system approach to model what is happening in the brain. So what people actually do is that they try to model the brain or try to replace what the brain is doing by using some models. And in this case, if we're interested in something that's a bit high dimensional, if we're looking at images or audio and more complex behavior, people usually look at deep recurrent neural networks, which is sequential models. They can basically approximate any kind of dynamical system. And they train them, so they give them these kind of stimulus that you would give the animal in these controlled experiments, and they try to train them to fit what you see, so either neural data or this kind of observations. And of course, most of these recurrent neural networks, the more expressive they are, the more black box they are. But one way to do it is to try to look at some of these dynamical motifs of these RNNs. So you can look at, there are some approaches for RNNs where you can actually look at fixed points or limit cycles and bifurcations, etc. And you can say something about the kind of computation that the brain is doing. So you can relate fixed points to memories or some limit cycles to a repetitive behavior, and so, or bifurcation to moving from one task to the other. So this is getting a bit closer, or at least people have shown some success for these kind of simple controlled experiments. Let's see. I think this decided to stop working now. Okay, so this doesn't work anymore. Let's see. Yeah. Okay. So the problem is that these simple kind of description, these fixed points and limit cycle are probably just a function of these simple tasks. So people find these if you have a simple task, but if you go to more complex naturalistic behavior, then probably these are not enough to explain. Neural dynamics, which is quite a rough terrain. So we have a lot of, it's a non-linear dynamical system. You have, it evolves across different temporal and spatial scales. You have partial observability, you're only observing a couple of neurons or a proxy of these recordings, while you do have billions of neurons, and you typically don't have enough data. And even if you have this data, it's quite noisy. So a different approach that we're looking into is to try to compare different models instead, and we treat this as trying to do generative modeling. So we assume that the data that we have are collected from some, or are sampled from some distribution, and we're trying to learn a similar distribution using our models rather than doing regression, and rather than starting from something like deep neural networks and then trying to explain that, try to go the other way around which is starting from well-understood models and then augment them if needed, if you need more complex networks, for example, to model your observations. So going towards hybrid models and mostly this SciML kind of models. And the last thing, we treat these models as SDEs because, as I said, it is quite complex dynamics. We're only observing a subset of the observations. And what we want to say is, if you view these kind of models as differential equations, you can view them as a spectrum from white box to black box models, where on one spectrum you have these kind of traditional differential equations where you know these kind of parameters and what each parameter mean. And on the other end, if you have a model that only have neural networks, you have neural differential equation, and you have this entire spectrum between them that you can fill. So this is the kind of models we're working on. We have some inputs, we have some outputs, and we have a hidden dynamical system that we try to infer. And what we're saying is we want to conceptualize these hidden dynamical systems as SDEs with some differentiable drift and diffusion terms. And these terms could come either from traditional models, or you could use also function approximators for them. But of course, the main question is, or the main challenge is, if you have something like this, like an SDE that has potentially some neural networks in them, is how can you infer these parameters in an efficient way? There isn't really like a standard approach or one way to do it, especially if you go into this kind of scale. So we heard about quasi-Monte Carlo approaches, or there's also adversarial approaches, but what we're trying to follow here is a method that is trying to do variational inference or amortized variational inference for these kind of SDs. I'm not going to go much into the details, but if you're interested, the method is in the package, and I can refer you to these papers. So we tested these. I think the conclusion also, this is some of the examples that we have in the notebook. So the conclusion is we try to test this on different data sets, and what we actually see is these kind of SDE models always work better than if you have ODEs, and even with much smaller models. So you end up with smaller latent states needed to fit the data than if you have an ODE, for example. We're also looking at different domains where you have these kind of problems, trying to fit SDEs to empirical data, try this into stochastic cloud Volterra models, and also some PKPD models as well. If you're interested, the package is now online, still in development mode, but at least for now, if you want to try it, there is a page online, and there's a documentation, and you can also read the paper if you're interested to know more. Yeah, thanks a lot.
Thank you. We have time for a couple questions. Yep.
Could you elaborate a bit more about the universal differential equations, like how couples with the neural systems?
So in the end, I think that's maybe which was the best slide to show this. So in the end, you have a dynamical system that you want to express, and you usually write these models as ODEs or SDEs. In our case, we think of them as SDEs, and this is more or less the way you can interpret universal differential equation. If you have neural networks in them, because neural networks are universal approximators, then there is this term that people have put on it, is that these are universal differential equations. And what I'm trying to say here is if you use this. Yeah. 1 second. If you think about differential equations in general, you can think of this universal differential equation as a spectrum between a traditional differential equation that doesn't have any kind of neural networks, and on the other end is just neural networks there, and that's what's called neural differential equation, which is people have been using mostly in the machine learning literature. And there's all this space in between these kind of extremes that you can exploit if you have some knowledge about the system that you can use or mix and match and stuff like this and test models in that way.
Thank you. All right.
Is one more? Or?
One more question. Sorry, we're a bit running out of time, but we can continue during the break.
Okay.
Thank you.
Yeah, thanks.
Our next speaker is Vincent from University of Bonn. He is going to tell us about how to use statistical methods applied to infectious disease using Julia.
Can you hear me? Hopefully. So yeah, thanks for the chance to show you one stochastic model of infectious disease. I think this does not work solely by me, but also with another PhD student from our group and a postdoc who unfortunately cannot be here, but I'm the one who has the pleasure to present to you. I think most of us, the pandemic hit us, and then we start doing epidemiological modeling. Nice. We love epidemiological models, and we did a lot of them, bunch of them, because we were involved in different consortia. And some of them, they used case count data. Some of them started to using wastewater data because people thought, okay, it would be really nice if we can use the wastewater to see how many infections are really there in the population, not only how many go to tests and getting reported. And then we started thinking, okay, now we have both data sources, so let's build a model that integrates both of them. And this is quite a challenging thing, and today I just want to show you what's the first part of the model, so the case count data model. We also have already done the second one, but that would be too much for 10 minutes. So let's look a bit about what our transmission model is, our ascertainment model, and how do we want to fit this to data we have at hand. So we're starting up with what is most important, the number of infections, stuff we don't see, but which is there. The number of infections, we say, okay, this is somehow Poisson distributed depending on our force of infection and the reproduction number of the disease. The reproduction number can change over time, so this might be Brownian motion, having some drift going up or down, depending on which stage we are of the disease, which prevention measures there are. And the force of infection is a weighted sum of how many people were already infected over the past 2 weeks. So how large is the force of me getting infected if I meet other people. Having the number of infections as a Poisson distributed random variable, we then can point from this number of infections to the next number of k days at which these infections might get potentially reported. So at which days people showing symptoms, at which days they then test themselves, and if they test themselves, there's a binomial distribution that this test is positive or did they already test, and so we end up with what we would observe, the number of reported infections. So this is the general modeling setup, so several steps, and what we then take as a state space are these 3 boxes, so number of infections per day for the last k days, the infections which are then potentially reported for the last k days, and the number of reported infections for the last k days. So 3 times k setting to 2 weeks make up like round about 42, 41 hidden variables which we need to fit later. There are some parameters also involved here. This weighted sum for the force of infection and the multinomial we take as the discretized gamma distribution, because we argue kind of that it's likely that symptoms occur after some days. So let's say between day 2 and 3, and then people are most likely to get tested and getting reported, and then it decreases again. And nearly no one directly tests when they get infected because they don't know yet. So there we have a shape and escape parameter for this distribution which we want to learn, and we want to learn this binomial parameter there, making up 3 parameters we want to fit with the state dimension of 41 in this case. And how do we do this? So in general, Bayesian inference for hidden Markov models, in this case, or hidden dynamic models, one way to do so is particle filtering. And the idea there is that we have hidden dynamics, our x, which is the state base of 41 different state variables. We have some kind of a transition law, so we know how to proceed from one time point to the next time point given the parameters, and we have some kind of readouts, and now we kind of know how they are, we have assumptions how they are related to our state space. And then in order to do Bayesian inference, we need to get the likelihood, and what this means is we need to calculate the probability of observing a data sequence given our parameter vector. And this means we need to integrate all possible unseen trajectories of this hidden states. So a lot of simulating and integrating out would be involved there. And the general idea how one can do is a particle marginal metropolis hastings or particle marginal MCMC methods, and they sample a parameter as you would do in a normal MCMC method, and they then approximate this likelihood by saying, okay, we take a number of particles at xt, we propagate them forward based on this transition law which we know, then we weight them based on how well they match our data, and having weighted them, we can resample them. So we don't propagate forward everything to the next time step, but only what was a nice trajectory, what fits our data well will be then used to propagate to the next time step xt+1, and then we start over and over again. So at the end, we end up with trajectories, and many trajectories, so and many possible hidden dynamics, but all of them are already in such a way that they kind of sorted by nicely fitting the data, and the sums and multiplying up all these weights then gives us an estimate on for this likelihood, actually an unbiased estimate, which is quite nice, so we can use the standard metropolis hastings algorithm and accept or reject our parameter theta and get a new parameter, sample new, do a new particle filter one, and so on and so on. So this is quite an intensive task to do. This is why Julia is quite nice, because this involves a lot of forward simulation steps, and this is where Julia is particularly fast in. So it's really something we don't want to do in Python. Having done this, the results look like that. Not good. So we get some kind of approximations of our posterior distribution of the parameters, and the 90% confidence interval cover our true values, but the distributions don't seem to be correct yet, and they seem kind of skewed, so there might be some structural things in there. But so we were starting to think, okay, how can we maybe inform this a bit better, because what we have this one area of case counts, but a huge dimension of states and a huge and some parameters we need to fit to this just one dimension of observables. So the idea is in this forward step that the particle filter does, we want to inform this forward propagation step already by the next data point, so that when we do resampling by weighting, don't put as many particles into the trash as we do right now, but we can reuse and get more unique trajectories, which then gives us better estimates. So we want to add somehow the distribution of the next hidden state given our next data point into this propagation step. And since we don't know this distribution, the idea is to use the neural network to learn this mapping or to learn this distribution, which we can then add on top of this particle filter. Right now, we're just trying to learn the mean and covariance metrics for a normal distribution there. Of course, given our model formulation, we should maybe add some different assumption here, but this is what we right now try to achieve, to make some kind what we call then simulation-informed neural network to generate posteriors with the guided particle filter. And to our knowledge, this is kind of new. So yeah, that was all. And if you have any ideas how to maybe improve this even more, or to use a different framework for the inference, let me know. I'm happy to take any suggestions and questions on that. Thank you.
Thank you. Any question? Yeah?
Thank you for the talk. Clearly very relevant and similar, right? You use similar methods. This PMMH, particle, what was the abbreviation?
Particle marginal metropolis hastings.
Particle marginal.
Because you use a particle filter to approximate the marginal likelihoods in the metropolis.
Would you say that would be useful anytime you have many agents and parameters for each? Kind of, that sounds like that was the point, that it would take too long to use just normal MCMC because there's so many, or is it wrong?
The point is it's useful if you have this kind of hidden dynamics which you don't know.
Yes.
So, and you want to integrate them out. But as soon as the hidden dynamics grow, this gets really, really slow. So
this gets really, okay.
So I in my experience, it doesn't scale that well with the number of states-based dimension as we would like it to have. So like having this dimension of 40 to 50 is already quite big. I tried it with 500 and it ran forever.
Okay. All right, I'll ask you more about this later.
Yep, sure.
Someone has questions.
Thanks.
So our next speaker will be talking about a very different topic. So we finished the biological science session. Then we'll start with the mathematical science session.
Let's see, is it mirroring right now? Yeah.
So our next speaker is April from Technical University Munich. And the topic is about numerical analysis using Julia package.
Okay, there we go. Perfect. Okay. Slightly late start. So I want to spend some time to discuss the concept of set-oriented numerics and specifically how these were implemented in Julia. There are a few different sort of entry points, a few different motivations which one might choose to sort of motivate the idea of set-oriented numerics. The one that I've chosen is the one that comes from my research, which is in dynamical systems. So I've prepared a short little example to show you. Let me pull it up here. And now you need to tell me if something is too small to see. Yeah. There we go. Now it's getting bigger. Better? Better, okay. So, I've prepared a small example. I have here a mapping known as the Henon map, which takes a point in 2 dimensions, maps it to another point in 2 dimensions, and one might sort of be interested in, well, okay, what do orbits of this mapping look like? If I just repeatedly iterate this mapping on one point, how does the point then evolve over time? And, well, we can test this a little bit with a small example. So I'll just run a little orbit starting at the point 1, 1 and going 10,000 steps into the future. And we can look at this evolution here. So lighter color here means that it's more recent. Darker is further in the past. And you see that it sort of follows this interesting, almost like parabolic looking shape. But it's extremely difficult to predict. One can prove that this model is chaotic in the sense that it has sensitive dependence on initial conditions. Any small error that one might make in the initial conditions, say by simply rounding, will compound to the point where orbits become completely uncorrelated to one another. What you can see, however, is that in spite of this correlation, there is still sort of global structure. There is this global structure in the sense that all of these orbits, despite being completely uncorrelated, still stay almost entirely within this sort of strange U shape here. And so you want to understand that a little bit more, why this is and what shape exactly this is. Because if you can understand where points end up, then in more complicated models, some sort of chemical model, a biomechanical model, whatever, you can find the sort of stable positions in which things will end up, right? Okay, so that's the sort of motivation for why one might be interested in dynamical systems, and more importantly in set-oriented numerics. Specifically, I've now added in, we have a continuous mapping from some d-dimensional space, and we just iterate the map over and over again. And we ask, well, what happens to some initial condition as we iterate further and further? And I unfortunately don't have, that's okay. These sort of global sinks that you find, or these points that tend to attract spaces, are called, naturally, attractors. These are points which sort of asymptotically all initial conditions move towards. And if the set which is attracting happens to be closed, then there is a very sort of nice mathematical formulation of the attractor, namely as an intersection of infinitely many iterations of some initial set. And this is essentially the beginning of the Gaio Global Analysis of Invariant Objects project. We say, okay, well, this representation here, we could quite easily, at least conceptually, try to implement this by saying, okay, we have some very coarse initial covering of the set. We map it forward. We make the covering in some sense finer by subdividing. We map it forward again. We continue over and over again until we get something which is within our tolerance. And this sort of very natural ansatz is how the Gaio project started, about 25 years ago now. I've added in the attractor algorithm here. It's exactly what I just mentioned. So we take some finite family of compact sets, we subdivide it in some way, we map the sets forward with whatever given mapping we have, and then we simply intersect with what already exists. And then there's a theorem that says, well, okay, after some, with some additional assumptions which I haven't mentioned, these families of compact sets in their union do, in fact, converge in Hausdorff metric to the attractor. Okay, so much for the sort of theoretical side of this. Now we can maybe try to implement this as some form of actual algorithm, right? Here I've added in a little bit of an intuition for what we want to do. So I've used the Henon map again as an example. We simply want to cover the initial attractor somehow. In this case, we're going to be using sort of squares, subdividing, mapping forward, subdividing, and so on and so on. Now, in order to do this, we want to sort of understand images of sets. So we're taking a function which is defined on points. We're now trying to understand what the image of a function on a set is. So we need some way to sort of compute this, right? Well, the easiest possible way that we could, try to implement this, maybe the most naive, but generally speaking, quite successful method, is to simply split the domain up into some grid of hypercubes. Okay? Each hypercube is a simple box, and together they partition up our phase space. And we can sort of use the Julia typing system now to our advantage. We're going to define sort of sets of these boxes by simply taking the existing Julia set objects and using them to store now the indices of our partition. And if we do this, then we already inherit a lot of the simple the simple operations that one might want to use on sets. Intersection, union is something, a subset of another thing, stuff like this is already built in. But we could also do, in some sense, some more fancy things, like being able to sample random points from within hypercubes. We can define ways in which we can cover a set of points with our hypercubes. And this will be how we make our cell mapping algorithm. So the sort of, in some sense, most naive way that one might want to map a set forward would be to just throw some test points into our set, map them forward with our given point map, and see where they land. And whatever boxes make up their landings, we call that the image. And we hope that that is somehow close to the true image, right? So these building blocks are, in that sense, then precisely what we need, and really all that we need, in order to do this sort of cell mapping. We can take a random point, we can map it forward, we can cover that point with some box, and the initial to final box, or the initial to, in some cases, multiple final boxes, is then our cell map. Very simple. Incredibly simple idea. And it's been done a couple of times. The initial first time was in the late 90s, I believe. And it was originally written in a very eclectic, difficult to understand C implementation. So I'm very happy that we don't have to look at that anymore. Okay, so we've set up all of the building blocks to compute these sort of set-wise images. Now we just need to put them together. And the method to do so is actually, it's simple enough that we can fit it into this slide. At this point, I'll mention that previous versions of Gaio, like that C version, if you look at the function which simply takes these test points and maps them forward, there would be no way that you could fit this into even 2 slides. It would be terribly ugly. So there's some beauty in how short and yet exactly performant Julia is. So we do exactly as we said. We take our initial source boxes, we sample some random test points, we map them forward, we cover them, and we reduce everything with unions. Okay. Now, if we do that, then, at this point I'll mention, okay, there are, of course, many optimizations that one can do. How you choose the test points can be done adaptively, depending on the, like, certain Lipschitz constants of the mapping. How you transform them to the specific boxes you need. Ensuring that your code, your LLVM code that you generate is type stable. Doing this, of course, on multiple threads, using Julia's macros. And of course, if you're going to do something on multiple threads, there's no reason why you couldn't also do it on a GPU. Okay, there are some reasons why you couldn't also do it on a GPU. But in this case, this is one of those examples where it's so simple that doing it on a GPU is virtually identical. So, I think it's time to try this. This algorithm, which I've added in here, comes from the initial paper from my PhD supervisor's PhD supervisor. So this algorithm was here 25 years ago, and this is the pseudocode which was written for this algorithm, as it was in that initial paper. And this here is the Julia implementation of the pseudocode. Again, there's something so satisfying, at least from a mathematician's point of view, that the initial pseudocode is so incredibly close to the Julia implementation. And this holds true for not just this sort of toy example algorithm, but indeed we've implemented many algorithms for these set-oriented numerical methods, and they all look like this. You can just copy-paste them essentially straight from the pseudocode. So, what do you say we try this here? Do a little live version of this. So we want to understand the attractor of this Henon mapping. So we're going to load the Gaio package, define ourselves our domain in 2 dimensions, partition the domain into a 2x2 grid, and then take our point map, convert it into a map that maps sets to sets, using this incredibly simple Monte Carlo implementation. And then we can implement our attractor algorithm exactly how you see it in the slides and in the pseudocode. We take our initial covering of the domain. So this is a covering of the entire 2x2 grid at this point. And we can simply do our algorithm for, let's say, 6 steps at first. And we can see what that looks like. Okay, still very rough covering. But if we do this maybe one more time, getting better, we start to see the structure a little bit. Let's go another time. Now things are looking a lot more understandable, a lot more like the initial scatter plot that we designed. This is generally the I should say workflow for these set-oriented methods, and I've presented one here. Obviously, there are many more, and there are other sort of ways into set-oriented numerics, be that multi-objective optimization, be that sort of coherent set understandings, and of course dynamical systems. Now, in the abstract for this talk, I did make some mention of Koopman operators. For those who know what this is, I may have added this in as a bit of, let's call it clickbait, for the Coop maniacs. I will show you how you could implement a transfer operator, the mathematical adjoint of the Koopman operator. We do this set-oriented way, which commonly goes under the name Ulam's method. I won't show the details for time, but if we do this, essentially what we're doing is we're taking, well, if we have partitions which act as sigma algebras, then if you have a sigma algebra, you obviously can define a measure. Right? You have a measurable set, you define a measure. If you have a measure and you have a mapping, then what is stopping you from looking at a push-forward measure? And essentially what this transfer operator does is it computes a discrete push-forward. Then you could ask yourself, well, what are the eigenvalues of this operator? And the eigenvalue, the fixed point of this operator, this is known in theory to sort of encode the statistical dynamics of a system. So areas with more mass given to them through this invariant measure, or this fixed point of this operator, are the areas in which points tend to stay in for longer during their trajectories. And areas with less mass tend to be less populated, if you look at one long trajectory. So what I can do now is if I take my initial transfer operator, I grab the leading eigenvector from this operator, and I look at, I've added in a little bit of a magnifying lens here, we see most of the points, or the most mass is on this sort of outer wing here, and this inner leg tends to get a lot less charge to it. And if we were to go back to the scatter plot that we saw earlier, that's essentially exactly what we saw. The older points were along this sort of intersection here. This area was darker. Along here, this area had many more light points. So indeed, we sort of rigorously cover the statistical behavior of the system, and we understand the statistics of this without ever needing to rely on sort of one long trajectory and sort of hoping that this has some sort of ergodic nature, hoping that this covers, in some sense, the typical dynamics of the system. So we can really boil down what is invariant, what is attracting, in order to sort of make global asymptotic statements about a system. Other systems which have been observed in this way include climate models, in order to understand sort of reef flow, molecules in biomedical situations have also been studied in order to simulate them to find sort of new medications. And at this point, I was going to stop. I was going to end the talk right here. I did, however, last weekend have 2 hours of extra time and a metal-capable GPU, which is, I mean, what else are you going to do on a weekend aside from coding in a little bit of GPU support? So I'll just show you very briefly. Here we go. So in the domain where computing the map, computing a single iteration of the map takes the most amount of time, where this is the bottleneck, parallelizing these methods becomes extremely, extremely useful. This is particularly the case in these biomedical models, where you have very high dimension, and understanding exactly what goes on takes already a simulation in of itself. So if you do that, and you code it in, I have here an example of a 3-dimensional attractor, where I'm simply looking at here. I am taking this ordinary differential equation. I am mapping it forward 1 unit of time using the standard Runge-Kutta 4th order method. And I'm going to do the exact same stuff as before to cover the attractor. And we can look at it very quickly. So it has a sort of interesting 4-wing structure. So what happens is points tend to sort of flow along these 2 larger wings, and then they spiral inward. So they flow out and then spiral inward. And of course, you can look at one individual trajectory and say, well, you know, probably most trajectories look like this, but you don't know for sure. So it would be nice to have actual rigorous statistics, and that's what these invariant measures provide. Is they provide rigorous statistics on what exactly the dynamics is in the system. And now I can finally show you, if I sort of artificially create the system where compute time is dominated by map evaluation, by simply reducing the step length of the Runge-Kutta method and making a lot more steps, so that it's a much more compute-intensive operation to integrate one time step. Then we see here I have the standard Monte Carlo method, which I'll let it run. In the test, this took something like 30 seconds, I think. So we have something like 30 seconds to sort of sit and relax and enjoy ourselves. It's been a long day, you know, we've seen a lot of talks. It's time to take a 30-second break. We can enjoy this. I honestly, to be real, I would have thought that it was done by now. I think the fact that I'm presenting it is making it take a little longer.
Meanwhile, any questions from the audience?
While it's going? Now it's going. Okay, 39 seconds. 39 seconds. Now let's try it with our metal-capable GPU. 2 seconds. Come on. That's pretty good. Okay, that was obviously a very quick sort of basic example, and in my initial testing, I haven't fully done serious benchmarks on this. In my initial testing, I have managed to reach a 100x performance boost by using the metal GPUs. And I have yet to actually saturate the GPU completely. So there is definitely still much more room upwards for performance gains. So thank you. Questions?
Can you explain again how you compute the eigenvalue?
The eigenvalues?
Yes.
Yes. So to keep it brief, the method which we use is commonly known as Ulam's method. Simply put, what we do is we look at each individual box, the pre-image of the box, the measure of the box intersected with its pre-image as a fraction of the initial box. If we do this for all of them, all pairs of boxes, what we get is a matrix, which represents the discretized push forward. And then we simply use whatever eigenvalue solver we want in order to compute this. So in this case, I used an Arnoldi method. And this is a Markov matrix, so we know that there's going to be a invariant object.
One last question.
Thanks. What would happen if there were 2 attractors in your initial box?
Mm-hmm. So the short answer is you would see 2 sets. You would see 2 sets in the plot. There is so I sort of went very briefly over, or I skipped entirely the sort of assumptions that you have to make on the system in order to have it converge in Hausdorff metric. But there is, at least in the dynamical systems literature, there is decompositions that one can make of a system into these sort of recurrent bits and, in a sense, gradient-like objects where there is no recurrent behavior. So the answer, what would happen if there's 2 attractors? Well, 2 attractors would show up and the rest would be gradient-like. Okay.
Great, thanks. We're running out of time, but if you guys want, you can catch up with a pro during the break. So thank you. Our next speaker is Manuel from Argentina, and he is going to talk about ODE system for sound synthesis applications.
Hello? Okay. Let me start this. Okay. Thank you for coming. Thanks, organizer. I will stay here because my remote mouse is not working. So, and I will have to use the mouse. I will talk about sonification or audification in real time of ordinary differential equations. That means take the solution of these equations and convert that to sound from two perspectives, as a pedagogical tool to explore the parameter space, the onset bifurcations, and transition to chaos, and also as a sound synthesis method, especially for some musical instrument models that we are working with. And this talk is also in joint with Antonio Ortega Bruc and Darío Ruiz from our group. It is the LabSol, the Acoustic and Sound Perception Lab at the University of Quilmes, Buenos Aires, Argentina. And this is also with the support of CONICET, that is the National Research Council. And this is the plan of the talk. Let's say this. Okay. So we have two parts. In the first part, in red, I will present the background of our project, who we are, what is our motivation, and then I will move into the explaining what are the advantages of translating the numerical solution of nonlinear dynamical system into sound, both from the pedagogical and from the mathematical modeling point of view, and also as a tool for sound synthesis. And then I will finish the first part presenting a small package that we recently developed. Actually, I think that it should be registered today, but we can try. I will give you the links at the end. And in the second part, in blue, depending on how much time is left, I will show you one or more examples with sound. And also, I will show you how to run this package from the REPL. Okay, then I will start commenting on my co-authors, Darío and Antonio. They are musicians and PhD candidates in our group. And with them, we are looking for modeling wind musical instruments from the paradigm of nonlinear dynamics. That means we try to extract the essential ingredients of the dynamics with minimal models, hopefully preserving some of the expressive capabilities of the original instruments. And we are interested, for example, in the link between some bifurcation in our mathematical model and some sonorities in the real instrument. For example, multiphonics in the saxophone, to get some insight on the process underlying this phenomena, but also because we want to make a digital replica of the instrument. And I would say we were talking a lot during the morning and about digital twins. I will not say digital twins because we are not interested in an exact copy of the sound. We are interested that the dynamical change of regimes are the same in the model and in the instrument. And to put this into test, we are working with musicians, interacting with the model in real time. Okay, and this is why we are interested for the moment with a computer model with a MIDI interface, but we are working with sensors in a mute instrument and eventually an embedded system. This is why we're interested in minimal models. And this project is also related to a more musical-oriented project with Martin Prosia. We were working with also with multiphonics in the saxophone, but more from a cognitive perspective. But now we are doing the psychophysical experiments with the package in Julia that I will present today. And finally, there's also a link with another project in our group that made a digital replica of the bandoneon, or bandoneon. I don't know if you know this is the emblematic instrument of tango, also of the city of my city. And there's a big problem because the bandoneons are really very difficult to manufacture and to obtain. Actually, most of the bandoneons that are around are almost 100 years old. So to have a digital replica is something that is really important. But for now, we are using for this project bandoneon 2.0 more classical sound synthesis methods, but we are working in a dynamical model of the free reed also. And finally, to finish the presentation of our group, I will say that this is framed in a more broad project or program that we can loosely call generalized lutherie, that goes beyond the digital lutherie, that the idea of a replica of a real instrument or to create new digital instrument is we are interested in many other ways that we can create sound and also modify sound while it's propagating through the air in a situation of musical performance. This has led us to work with, for example, acoustic metamaterials as an extension of musical instrument that can work at the scale of a room. For example, the sonic crystal room can modify the sound that is emitted from an orchestra or from singers. And we are not only doing scientific research, but also we made an opera that will be re-released in next September. Okay, so coming back to our motivation, and in my particular case, my background I'm a physicist, and my background is in applied nonlinear dynamical system and acoustics. So the idea to join these two worlds has a long history. And at the beginning of the 2000s, I was working with my former advisor, Gabriel Mindlin, and a colleague, Marcos Trevisan. We were working in dynamical models of the vocal folds for speaker recognition. And then Gabriel developed further the model and for birdsong, and now his group is one of the leading reference in this field, and is still for me a source of inspiration. And more recently, I get involved in a more pedagogical part of the nonlinear dynamical system, in a more broader project of acoustic education that was led by Gabriel Catren of the University of Paris. And in that photo, it's a workshop, not only in the academia, it's in the wild. We gave a workshop in the context of an art residence that was called Deeply Organized Chaos, and it was done entirely in Julia and Pluto. And we end that workshop with a jam session making sound from ODEs. Unfortunately, but at that moment, we used Super Collider because this package was not yet developed. But I take this experience because for people that have no mathematical training, the possibility to play with the model and to make sound is a really nice way to approach to this kind of problem. So this idea, this experience, together with the need of the model exploration for the mathematical model of the musical instrument, lead us to try to develop the package that we'll present today. that the idea is not only to have this intuitive access, but also that, for example, for some model of the musical instrument, I will show you at the end a model of the of a saxophone. For example, the parameters are the blowing pressure and the pressure of the lips on the mouthpiece. So we can control these parameters, and the musicians can have a more intuitive interaction with these parameters. And of course, also this can be used also for sound synthesis and live coding. Okay, there are many advantages of using ODEs as a sound synthesis. I will only say here that you have the more traditional model, methods that are like FM or granular synthesis that work extremely well. They're extremely effective, but not always have some relation with the acoustical phenomena. And on the other side, you have models that are physically based, but are much more expensive in terms of computation. The idea is that the models based on ODEs can stay in between, having advantages both. And then we start to develop this idea of making sound with ODEs with the two most powerful platforms for sound synthesis, that are Super Collider and MaxMSP. In the case of Super Collider, we use a library that was developed by Daniel Meyer as the one sample feedback that implement a fixed step, because you know in audio you have the sampling rate, so you need the solution at fixed steps. And also in MaxMSP, we implemented an object that was written in C that it takes the Runge-Kutta and with fixed step. And here we are taking the numerical algorithm to the domain of the software used for sound synthesis. The idea is going to other way around, giving the power to Julia to real sound capabilities. Of course, using this wonderful library, I think that it's not necessary to explain that the algorithms that have differential equations are extremely efficient. And we also join this with port audio, that the idea is to use port audio to call the solvers of differential equation in a dedicated audio thread that is managed by port audio. Okay. So this are the main features of the package. The idea is to use differential equation.jl and leave. We at the beginning we start to use there is a library that's called portaudio.jl, but the problem is that it's not easy to access to the asynchronous callbacks that are necessary for audio, because you need to refill the audio buffer as soon as you need. Okay. So we use the wrapper of the port audio that exists already in Julia. There's port audio JLL, and the idea is that the main structure is the DE source, that it acts like like a ODE problem in the sense that it receives a function that defines the problem, or two functions in the case of stochastic differential equation. The second function is the noise, and also receive an array of initial conditions, an array of parameters, and stores this D problem, also a callback for port audio, and the state between callbacks. Okay, and then the idea is that when we make sound from this the source using start the source, and that creates a port audio stream, and the callback asynchronously invoke solve to refill the audio buffer. We also try at the beginning. We thought that maybe using the integrator interface was more efficient. but we made some tests, and the solve is higher level, but it works well for our purpose. And the good thing is that we can change the parameters on the fly. Okay, not only the parameters of the problem, but also there's channel mapping that we say which variables of the model are mapping to which audio outputs. Okay, and also there's a time scaling, of course, because the time in the differential equation is not related to the real time. So we can make a short demonstration here. So we are using real-time audio diff ec, and we define a function. In this case, it's a very simple differential system of two differential equations that it's based on the Rayleigh model of a reed of a clarinet. So it's just a nonlinear dissipation there, and some negative dissipation, and a nonlinear dissipation of cubic. And then we can define our source, invoking the source, the function, and a set of initial conditions and two parameters. The two parameters of the model are: the first one is the parameter that when cross the zero, you get a Hopf bifurcation. So now we start with the system off. And the second parameter is the elastic constant. So it will control the square root of this, it will relate it to the frequency. Okay, so now it's defined, and then we can start our source and with the default output device, but we cannot listen because this time scaling now it's we need to rescale the time. So we set the scaling to 1000. That means that a time of 1 in the model is 1 millisecond. So it's in the audio rate. Okay. Now we will set the first parameter, that is the bifurcation, to the positive value, and hopefully we will hear something. No. Let's see what happened. We try this, and okay, that's strange. We try with this. Sorry. It's working, right, with this? Okay, for some reason. Yeah, but for some reason. Okay, very loud. Okay, we will switch to the. Maybe I need to do again in the REPL, but here in the Pluto notebook we have the same. But we check here, maybe it's something with the default output device. Here we have a two-system couple. This is a Duffing oscillator, and it's coupled to a Van der Pol oscillator. So now the coupling is 0. so there's no oscillation. We will move the time scaling. Oops. And then get some excitation from the van der Pol. This is the coupling, and then I will start to move the time scaling to some. I will lower the sound because it's. And then we can control, for example, this is the time scale of the van der Pol. Okay, now we can move to lower frequencies. And increase the coupling. And eventually we can find periodic orbits. These parameters controls, but here we can change the mapping. These are the variables of the Duffin oscillator, but we can see the van der Pol. Okay. Now we are in a very far from the Hopf bifurcation. Here, some more soft sound, and also lower. And here I get higher harmonics. Then the effect on the Duffin oscillator is much more. Okay. Then if I decrease this, is more close to the typical forced Duffin oscillator with a periodic orbit. Okay. Then it's more easy to find periodic orbits in the system. Okay, so I will finish showing you very briefly the model of the saxophone. This model has 18 equations because it's with the modes of the tube, and also some variables for the movement of the reed and a coupling, linear coupling between the movement of the reed and the pressure in the saxophone. So we will start here. Now this parameter controls the blowing pressure. I can increase this. Probably we need to. Yeah, probably we need to. That was the problem before. Okay. We have to redefine the source. Okay. We were trying to get some multiphonics now. This is a Neymar-Sacker bifurcation in the model. I have a periodic orbit that has a Hopf inside, so I have a torus. It's a quasi-periodic behavior, and this is something that jazz musicians do, like, you know. And then you have this octave leap. Of course, there's some multi-stability in the model, and when you switch from one mode to the other, you have this behavior, and here you can explore the different modes. This is the first mode, and this in the right channel, the second, the third one. There's a non-linear interaction between the first mode and the third mode. This is why it happens. tremolo. Okay? And then I will switch off. Okay, thank you.
Thank you very much. Somebody have any questions?
The question is, does this the real-time synthesis also lend itself to including a more complex model of, say, the human oral cavity, which
Yes, of course. And in fact, I show you one kind of multiphonic. For other type of multiphonic, you need to add the coupling with the vocal tract.
Right. Absolutely.
Yeah. We are on that.
Like I play, so I know what it
yeah,
could sound
it's
like.
Really
right?
important.
I think this real-time synthesis is really impressive, and the sound is actually quite accurate.
Okay.
Any questions? Thank you.
Okay. Thank you.
He's going to tell us about how to solve fractional differential equations using Julia.
So, okay.
So hi everyone, this is Qinyu. So today my talk will focus on the solve fractional differential equations with my developed package fractional difficult.gl and some recent advances in boundary value problem solving in the SciML universe. Okay. So I'm currently a master student at Zhejiang University. Also in the past year, I am the GSOC student, and in this year, we received the NumFocus small development grant to develop the boundary value differential algebraic equation solvers. Yeah. So next. So my talk will divide into 3 parts. So first, let's see how to solve a fractional differential equations with fractional difficult.gl. Okay. Okay. So nature's always like behaving a fractional order way. So some research found that instead of using the usual differentiation or Euro integral, fractional differential equations, fractional differentiation and fractional integral can usually better describe the word, right? So from the, for example, the Kirchhoff circular law or the to the Newtonian mechanics. So the fractional order differentiation can introduce us to the fractional differential equations. As for the multi-order fractional differential equation system, fractional difficult.jl has the most solver available for this kind of problems, like the commensurate order or the non-commensurate order. During the recent refactors, fractional difficult.jl can handle similarly with the ordinary difficult.jl, like solving the fractional ordinary differential equations. Like we have several solvers, like the product integration rules and fractional linear multi-steps methods. So let's take a look at the numerical example here. So to model a multi-order system, we just need to follow the design pattern of the ordinary differential, like the ordinary difficult.jl. So we can see the code here. We need to define its right-hand side and its time interval, the initial condition, and the fractional orders, right? So we can directly call this solve function and use some appropriate solver. So yeah, we can get the numerical solution of our fractional ordinary differential equation model. So yeah, next we can fractional difficult.jl can also handle the linear multi-terms fractional ordinary differential equation. The currently supported solvers are the product integration rules solvers. So there are explicit ones and implicit ones. So we can directly see the numerical example here. So to have a more intuitive, so we can see here with the initial conditions specified as here, we can just follow the design pattern from the previous section. So we can construct a model and call this solver to solve our that's this kind of linear multi-terms FODE, right? And we can use the numerical solver to solve this linear multi-terms problem. And also, fractional difficult.jl also has a good support for fractional delay differential equations. Both single leg and multiple legs is also supported. They utilize the predictor corrector methods to obtain a high precision numerical solution of the fractional delay differential equation. So we would directly see an relatively easy example here. Solving fractional delay differential equations is also similar with the delay difficult.jl. We need to construct our FDTD problem and call the corresponding solver to solve this problem. Here are the system. Here are the people growth model. We can use instead of using the delay differential equations, we can use the fractional order delay differential equation to have a better describe of this people growth model. And the future plans of the package fractional difficult.jl, because it's part of my free time contribution to the Julia ecosystem. So I think maybe next time we should add more powerful solvers. And the internals of the solvers are not very are kind of clumsy. So we should refactor the whole package and provide a high performance one solvers. So next is the recent progress of the BVP solving in the SciML universe. Okay, this chart is made by Chris Rikakis. I believe many of you may be familiar with the differential equation solving ecosystem in Julia and SciML stack. So as the most powerful DiffEq suite, differential equations.jl can handle many kinds of problems like solving ODE, DDE, SDE, make solving these equations so much easy. However, as for the boundary value problem solving, differential equations.jl's capability is relatively just ordinary and lack the powerful solvers tailored for this kind of problem. So currently, the popular BVP solvers like BVP4C, BVP5C, and BVP solver in SciPy all are using the collocation methods to achieve a better performance. So in this case, differential equations.jl capability for BVP problem solving is lagged behind MATLAB and like SciPy. But luckily, all this situation is just as the table was made. The situation has gotten better in the current status. Boundary value problems are a very important kind of mathematical model, playing an important role in physics and economics, etc. A boundary value problem is actually an ODE, but just with some more constraints among the whole time interval. We can see the classical example is the swirling flow problem and the best launching problems in optimal control. All of this is just solving a large boundary value problems. So let's start with what we are already familiar. The explicit Runge-Kutta method and the implicit Runge-Kutta method. As for the explicit Runge-Kutta method, we have the Butcher table, right? Each Butcher table can define a explicit Runge-Kutta method. We have the coefficients. We just have the and we have the discrete stage computing equations. So a very easy implementation would be do a for loop and utilize these parameters and the equation. We can solve our problem in a very simple way, like the most simple solver as a let's say Euler methods, right? So and to our most familiar with like RK4 or DP5. Another one like the implicit Runge-Kutta methods. We also have their Butcher table, which can define we have their Butcher table, which is the coefficients in the solver. Similar to the explicit Runge-Kutta method, implicit Runge-Kutta method also have the discrete stage computing equations, but different from the explicit Runge-Kutta method, it needs to construct a nonlinear system to solve our to represent the discrete stage computing, and we just need to call the nonlinear solve to solve this nonlinear system. We can get our numerical solutions. However, when encountering with boundary value problems, we need to use the monotonic implicit Runge-Kutta methods. The deploy of the monotonic implicit numerical method can be briefly summarized as the following steps. So firstly, we need to discretize the whole time interval, and in every sub-interval, we can construct the collocation equation using the Boucher table and formulate the collocation equation to a large nonlinear system and call the nonlinear solvers like the recent advance in nonlinear solver, like the nonlinear solve.gl, right? So we can call nonlinear solve.gl, use our nonlinear solve like a solver, like a Newton-Raphson or trust region method to solve our nonlinear system. Then we can get the numerical solution of the boundary value problems. Yeah. So after the nonlinear solve part, we only get the discrete solution of the boundary value problems. During the whole nonlinear solve process, we can take advantage of the powerful SML tools like sparse diff tools.gl. Since our constructed nonlinear system is a almost banded structure, we can directly use the banded matrices.gl and fast almost banded matrix.gl to accelerate our nonlinear system solving. So all this is just the purely solving part of the work methods. In the context of solving differential equations, the error is an important term for, like you said, let's say, evaluating the obtained numerical solutions and assessing the trustability of our model, right? Here we need to distinguish the defect control and error control. First, we can easily understand the global error here. It's just the difference between the analytical solutions and our numerical solutions from the global error is just the difference between the analytical solution and the numerical solution. But the defect is actually the measurement of how the numerical solutions fail to satisfy the original differential equations. Like the packages use defect control is like BVP4C and BVP5C in MATLAB and MERCDC BVP solver in Fortran. So in the 2023 GSOC project, I implemented the defect control adaptivity for the work methods. The basic working flow can be checked from the broken numerical solution of boundary value problems, or you can just check out the GitHub PR for the details of implementing this this feature. Yeah. The reason we need the adaptivity is that for any numerical algorithms, if we want a numerical solution, we need our mesh be pretty small to get a higher accuracy. But on the other hand, to improve the accuracy of our numerical solution, we need to the performance may be fallen, right? It comes to the opposite part. We want to improve our performance. We need to use a Croarson grid to, accelerating the whole solving process. But in this case, the accuracy may be also fallen. So the defect control adaptivity here is to achieve the balance between accuracy and efficiency. So the core of the defect control adaptivity is according to the computing defect. The defect is just the measurement of how the numerical solution from nonlinear solving fail to satisfy the original differential equation. After we get the defect of our original numerical solution, we can, according to the defect, we decide to refine our mesh and get a and make the accuracy and performance. So here is an easy boundary value problem example, which satisfies the boundary conditions. We can convert it to a first order problem. So this is just a simple boundary value problem. We set the adaptive keyword argument to be true, so we can turn on the defect control adaptivity in the numerical solver. Then we can get a control of the accuracy and the performance of our numerical solution. Apart from Merck methods, we can also use the shooting methods to solve boundary value problems. The shooting method is also a BOAP solving method, which converts the BOAP to IVP and hence form a it also construct a nonlinear system, but it achieves the BOAP solving by adjusting the initial value of the nonlinear system to solve this whole boundary value problem. Differential equation.jl or the whole stack of SciML universe have the similar API, right? So we just create a problem, call a solver to solve it, and we can plot the numerical solution. So that's all. That's how we solve a differential equation. Similarly, boundary value diffq.jl also has the same constructor for the boundary value problems. We have a BOAP problem for general multi-point boundary value problems constructor, and let's say the 2-point BOAP problem for just boundary value problems has the constraint in the start and in the end in the time interval. After the implementation of the defect control adaptivity, we run some benchmarks for the implemented Merck methods and shooting methods against the Fortran's solver, like a BOAP solver and a BOAP M2. So we can see from the benchmark here, the Merck solvers in boundary value diffq.jl is pretty fast. It achieves both accuracy and performance in the numerical solving. Before we go any further, we need to learn some basic ideas of Runge-Kutta-Nystrom methods for second order initial value problems. Instead of directly transforming the second order IVP to several first order ones, we can directly use RKN methods. That's the Runge-Kutta-Nystrom methods to solve the second order initial value problem. For example, we have a second order IVP with the initial value and the derivative of the initial value problem. Similarly, we can all we need is the Butcher table and the computing of the discrete stages, and then we can process the iterative computing during the whole discretized mesh, and we can get the numerical solution of a second order initial value problem. In the BOP solving part, we also have this kind of Nystrom method. It's called monotonic implicit Roncourt Nystrom methods. It has a similar idea of the previous Merck methods. With the Butcher table, we first need to discretize our second order BOP problem and construct the nonlinear system so that we can directly call the nonlinear solver to solve our nonlinear system, and we can get the numerical solution. For example, if we want to solve this second order BOP problem with such 6 boundary constraints, we can just write our model in a similar style and call the Mercklian methods from boundary value diffq.jl to solve this BOP system directly, and then we can have the numerical solutions on the right side. Okay. Differential equations.jl, the package. The second order BOP problem constructor and 2-point second order BOP problem constructor is similar with the previous first order one. Just some okay. Next is the non-focused mode development grant progress. So let's say a boundary value differential algebraic equation have the separated form of a combination of differential and algebraic equations with boundary conditions specified at both ends or among the time interval. For example, in optimal control or parameter estimation, etc., boundary value differential algebraic equations always show up. Like the right-hand side hydrodynamic semiconductor equations, here is an index 1 boundary value differential algebraic equation. BDF and certain implicit Roncourt method can behave very well on the initial value DAE. This method might cause the instability when solving a boundary value kind of differential algebraic equations. So we need our native BVDAE solver in the SciML universe. Let's see a horizontal comparison of the current BVDAE solvers. Let's say the MATLAB and Mathematica doesn't have such boundary value differential algebraic equation solver, and Fortran only has the core DAE solver for these kind of problems. Python or R just interfacing from Fortran to solve these kind of problems. In Julia or in SciML, we decide to implement our native boundary value differential algebraic equations to support this kind of problem solving. So the basic idea of solving this boundary value differential algebraic equation is just the collocation methods for boundary for this kind of problems. We need to build a nonlinear system in the collocation points and deploy the Newton iteration methods to solve this large nonlinear system. Here we will dive into the detail of these methods. First, we have this K stage collocation K stage collocation points. Yeah. According to the monomial representation for piecewise approximation, we can set up the collocation equations in these collocation points. And then substitute the monomial representation. We can get the nonlinear system. All we left to do is just solving this system. We can get the numerical solution of this index 1 differential algebraic equation. So during the discretizing process, we need to solve this. We need to solve this linear system. This linear system is not just banded or block diagonal. It's more of a almost block diagonal matrices. It's similar to the block diagonal, but they have some overlapping in the during the adjacent corner. So in order to solve this kind of linear systems, we developed the Julia package like almost block diagonals.jl to solve this kind of linear system. The details of solving this kind of almost block diagonal system is instead we directly solving it. It would be we can transform the almost block diagonal system by we add a random row in the first row of each block matrix, and we divide this we divide this matrix into like we divide each one, and we factorize one by one, so we can get the factorized form of this matrix. Next, if we want to solve this linear system, we just use the forward substitution or the backward substitution to just get the numerical solution of this linear system. Yeah. So here is a easy numerical boundary value differential algebraic equation example. It's just an index 1 BVDAE problem with the boundary conditions specified as follow. So during the past several months working, it is already can successfully solving this. It can already successfully solving this problem. But as for the higher index 1 or like say index 2, index 3, the initial condition case we can directly using the modeling toolkit to let's say decrease our index and directly solving using ordinary diffq.jl. In the boundary value case, we need to implement such projected. It's in the future plan. Yeah, we need to implement such projected collocation methods to let's say it's just in the subinterval the project implicit collocation method just project the solution in the end of each subinterval and complete the solving process. So in the future plans of this non-focus project, we plan to refactor the current implementation. Just the subroutine is just complex, so we need to clean this subroutine as much as possible. Also implement the support for index to BVDE problem solving and such benchmarks for just from Fortran or from Python or from R. Yeah. Okay. Yeah. That's
Thank
all.
you.
Thank you very much. Thank you very much.
Thank you. Maybe
Yeah.
just one quick question, if there's any. Okay, one question, and the rest, I guess you're available during the break, right? So we can continue discussing. Yeah.
Thanks for the talk. I have a question regarding your fractional derivatives.
Yeah.
There are different flavors of fractional derivatives. For instance, you have Caputo derivatives. Or like what kind? How do you decide? I mean, these are actually different. For instance, for Riemann-Liouville, when you take a derivative of a constant, you basically get nonlinear terms there, so it doesn't.
Yeah, that's a good question. The most used case is the Caputo one, right? So in the fractional difficult.jl, we only support the Caputo sense of fractional derivative, fractional differential equations solving. Yeah.
Can I ask one more question? What about the stochastic fractional derivatives? Like when you have stochastic differential equations.
Yeah. I know. That's in the future plans, but currently it doesn't support. Yeah.
Let's thank the speaker again.
Yeah. Thank you.
All right. Thanks, everyone. That will conclude this afternoon's session.